So the first speaker in the afternoon session is Fumi Nobu Takahashi from Tohoku University, and he's going to talk on Qcdxim dark matter in the presence of peptide coinsymmetric breaking. Okay, Fumi, are you ready?
Yes.
Please start.
Thank you. First of all, I just thank the organizers for invitation. I'm very happy to be able to talk and attend this workshop. And this talk is based on the work in collaboration with Qcdxim from Busan University and Shota Nakagawa and Kohen Masukawa. So these two are my graduate students. Okay, so let me I can quickly go through the first part of introduction. So we don't know why the strong CP variety effect is so small. And this is the theta term in QCD, which explicitly violates both parity and CP symmetries, and therefore it contributes to neutral EDM. However, to satisfy the current bound, the theta parameter appearing here must satisfy this very tight bound. It must be smaller than about 10 to minus 10. And well, precisely speaking, this is the effective theta parameter taking account of the quark mass phases. But such a small parameter in the Lagrangian is a puzzle, and which is known as the strong CP problem. And one of the plausible solutions to this strong CP problem is the peptide mechanism that predicts the QCD axiom. And the most essential part of the peptide mechanism is the assumption of the U1 peak symmetry. So this U1 peak symmetry must be pointers broken, and it is expressly broken only by QCD. And the other peak symmetry breaking terms must be absent or suppressed very much. And in this case, axion is coupled to gluons, and the axion acquires a potential through the interaction. So in effect, the theta parameter is promoted to the axion field, and axion acquires potential from this interaction. And when it is stabilized at potential minimum, the CP phase is dynamically set to 0. So this green line represents the axion potential at temperatures lower than QCD scale. And as you can see, the axion will be stabilized here, where the CP phase vanishes. On the other hand, at temperatures higher than QCD scale, the axion potential practically vanishes, and the axion is almost massless in the very early universe. And this is axion mass at the 0 temperature, MA, 0, and this is related to the decay constant FA. And if FA is around GB, the mass is about 6 micro electron volt. And for such ultralight mass, the axion is stable on the cosmological time scale. So once produced, it will contribute to dark matter. And the right amount of axion dark matter can be generated by the so-called misalignment mechanism. So as I said, the QCD axion can solve the strong CP problem dynamically. So it means that wherever it initially is, it will stabilize at the potential minimum, and it starts to oscillate when the curvature of the potential becomes comparable to the hyperparameter. And then it starts to oscillate about this CP conserving minimum, and this oscillation energy becomes dark matter. And the axion abundance is related to the decay constant by this equation. And the theta initial, this is the initial misalignment angle. The most natural value is over the unity. And for FA around 10 to 12 GB, you can explain dark matter density for theta initial angle over the unity. Here, capital F is the harmonic effect. If initial angle is close to the top of the potential, namely close to pi, then here the first derivative of the potential is suppressed. So it takes a bit longer time for the axion to start oscillating. And because the potential grows during QCD phase transition, the potential energy increases if the onset of oscillation is delayed. So that kind of effect is taken into account by this function F. And for FA around 10 to 12 GB, you can explain all dark matter by the QCD axiom produced by the misalignment mechanism. And this argument sets the upper end of the so-called classical axion window. And the lower end comes from the stellar cooling argument, such as neutron stars. And in the case of Qcdxim, mass and decay constant are one-to-one correspondence. So corresponding mass is in the range of micro EV and 10 milli-electron volt. And if it is close to 1 micro-electron volt, you can explain dark matter by the misalignment mechanism naturally. So this figure, so I took this nice-looking figure from this web page, and this shows the current bounds on the axion photon coupling, usually denoted by GA gamma, as a function of axion mass ranging from 10 to the 12 eV up to 10 MeV. So these shaded regions are excluded by various observations or experiments, and some of them assume that the dark matter density is explained by axiom. And here, this yellowish region represents the axiom mass over the 1 micro-electron volt, where you can explain dark matter naturally. But as you can see here, there are many experiments targeting at heavier axiom masses or light axiom masses. Okay. So the question is, how can we produce axiom dark matter in those regions, heavier or lighter than micro-electron volt? So one way to produce the right amount of dark matter for the axiom mass lighter than micro EV is to allow fine-tuning of the initial angle, theta initial, to be less than unity. If you look at this formula of the axion density, if you allow theta initial to be much smaller than unity, you can allow the decay constant much larger than 10 to 12 GeV. So the axiom can be much lighter than micro EV. For instance, if initial angle is around 10 to the minus 3 or so, the axial decay constant can be as large as 10 to 16 or 17 GeV. Okay. So by the way, this amount of fine-tuning can be relaxed if you consider the inflation scale with hyperparameter less than QCD scale, because in that case, axiom will acquire the potential already during inflation. And by considering stochastic dynamics, the initial angle is can be naturally much smaller than unity. So here, if we assume here it is implicit assume that inflation scale is much higher than QCD scale. On the other hand, in order to generate the right amount of dark matter for the axiom mass heavier than micro EV, we need to one way is to put the axiom very close to the top of the potential. So in other words, initial misalignment angle close to pi. In this case, as I mentioned earlier, by making use of the unharmonic effect, axiom abundance can be enhanced. As you can see from this fitted formula for the unharmonic function, if theta initial is close to pi, this function can be much larger than unity, so the axiom abundance can be enhanced. However, this enhancement is only logarithmic. So if you want to enhance the axiom abundance by many orders of magnitude, you would need very much fine-tuning of theta angle, okay, initial theta parameter. And it means that the final axion density is very sensitive to the initial choice of the axion field value. Okay. Even if initial field value is slightly deviated from pi, it will soon start to oscillate about potential minimum when the curvature becomes comparable to the hyperparameter. So you need very much fine-tuning of theta. So in other words, axion density becomes very sensitive to the initial choice of this angle. It is okay as long as you consider the classical motion of the axiom, but in fact, if you take account of the total fluctuation of the axiom, it leads to the ice curvature perturbation, and such a sensitive, if the axiom abundance is very sensitive to the initial choice of angle, it means that ice curvature perturbation, as well as its non-gravity sanity, get extremely enhanced. So I took this figure from my old paper, and Well, actually, before this paper, there was some confusion about the behavior of ice curvature perturbation in the hilltop limit. So we corrected this confusion in this paper. Anyway, here we show the upper bound on the hyperparameter during inflation as a function of FA. So if the axiom explains all dark matter, so this is upper bound on hyperparameter. So as you can see, if FA is around 10 to 12 GB or 10 to 14 GB, the upper bound on inflation scale is about 10 to 7, so 10 to 8 GB. However, if you go to smaller values of FA, you need to put the axiom very close to the top of the potential, so that due to the harmonic effect, ice curvature bound becomes very tight, and the hyperparameter must be very small as FA becomes smaller than 10 to 10 GB as well. And another way to produce the axiom with mass heavier than micro EV is to use the decay of topological defects, such as axiom cosmic string or domain walls. And there are many works about on this subject. And so there's still under debate which value of decay constant is necessary to produce the right amount of axiom dark matter. But probably the FA around 10 to 10 GeV or so is required. And it is probably unlikely to explain all dark matter for FA as small as 10 to 8 GeV. And here, let me briefly comment on this issue. And many works assumes that the PQ scalar or PQ sector is very simple. That consists of a single complex PQ scalar. And however, the string wall network probably depends on the UV completion. And as an extreme example, let me mention the clockwork axiom model or alignment axiom model, which is an extended version of the famous Kim-Niels-Pearson mechanism. So let me introduce N complex PQ scalar field, phi I, which develop non-zero VEV in the low energy. And we also assign charges in such a way that symmetry breaking terms shown here are allowed. Then initially we have N global U1 symmetries of each phi I, but N-1 of the N U1 symmetries are expressly broken by this breaking term shown in the second line. Then in the low energy, we are left with single unbroken U1 symmetry, which is identified with U1 PQ symmetry. In this setup, the axiom decay constant FA is related to the VEV or symmetry breaking scale of U1, here denoted by F, by this relation. And as you can see, with this setup, you can have huge hierarchy between the axiom decay constant and actual symmetry breaking scales. And in this setup, so the phase transition occurs at a temperature comparable to F, which can be much smaller than FA. So the symmetry restoration is more likely in this setup. And moreover, the strings and walls form very complicated setup, complicated network in this setup. And of course, if you integrate all the heavy degrees of freedom, we are left with single axiom with decay constant FA. So we should have some configuration of strings and walls in the UV theory that corresponds to the ordinary cosmic string. And this is the configuration. For instance, in the case of n equal 2, 3 cosmic string of phi 1 is connected to cosmic string of phi 2 by domain walls like this. And if n equals 3, the situation becomes more complicated. 3 phi 1 cosmic strings are connected to 1 phi 2 cosmic string, and 3 phi 2 cosmic strings are connected to phi 3 cosmic string. And you can see how complicated it would be if you change the number of n equals 3 to n equal 15 or 20. But actually, you can calculate the tension of this complicated set of strings and walls here denoted by string bundles. And if you can calculate this tension, and it turns out to be equal to the tension of ordinary cosmic string with decay constant FA. So this is the object that corresponds to the ordinary cosmic string. And usually we don't care about the structure inside the core of cosmic string. And of course, if you have complicated UV sector, the internal structure can be complicated. That's fine. However, the question is, are these complicated string bundles with complicated internal structure are really formed in the actual history of the universe? That is totally different question. And so we have studied this in this paper. And we also performed a simple numerical calculations. And it turns out probably these complete string bundles are not formed in the actual evolution of the universe. So this can be understood by noting that in order to have these string bundles, you need to have huge hierarchy in numbers of different kinds of strings. But when first cosmic strings are formed, they quickly follow the scaling solution. So each cosmic string exists, so one or two cosmic strings exist per horizon. So number density is same on average. However, in order to form this complicated structure, you would need exponential hierarchy in the numbers of different kinds of cosmic strings. So in that case, the string wall network are kind of frustrated, and it does not follow the scaling solution. So its energy density can be higher than the scaling solution. It may produce more axioms, and moreover, when it collapses, it may produce gravitational waves in the nanohertz frequencies, which may be within the pulsar timing array. Okay, coming back to the quality problem. So the essential assumption is that PQ symmetry is a good symmetry, and it's only broken by QCD. But it is widely believed that the global symmetries are explicitly broken in the quantum gravity theory. So there may be other breaking terms of UM-PQ symmetry. However, if it exists, its size must be very much suppressed to satisfy the neutron EDM bound. And there are many works that study the effect of the extra peak breaking on the QCD axiom, but many of them assume the symmetry breaking. In other words, in our universe, extra peak breaking is large, but somehow it's time dependent, and in the low energy, especially in the current universe, its size is very much suppressed. But in this recent paper, we studied the cosmological effect of time-independent extra peak breaking term, and such a time-independent extra peak breaking term can be generated, for instance, by the coupling of axiom to non-abelian case symmetry, or by introducing high dimension operator of the PQ scalars. And as I will see shortly, we find that the axiom abundance can be either enhanced or reduced significantly, depending on initial condition. And in particular, the axiom can explain all dark matter for any values of FA. So it can be as low as the lower end of the classical axiom window, if you allow a mild fine tuning. Okay, so one of the reasons why this time independent peak breaking can have significant impact on the QCD axiom dynamics is that the potential coming from QCD becomes vanishingly small at high temperatures. So this temperature dependence can be calculated by the lattice QCD, and so this can be well fitted by this equation. And as you can see from this figure, when the temperature is high, the axiom mass is very small, but as temperature decreases, the axiom mass increases rapidly and becomes more or less constant at temperatures below 150 MeV. And now we introduce the extra peak breaking term parameterized by this. And here, lambda h is the dynamical scale that generates this potential. And n is an integer, or it can be a rational number in the more general context. and theta h is a relative phase between this peaky breaking term and the potential coming from QCD. If theta h is 0, then both terms have the minimum at the origin, and there will be no bound on the size of peaky breaking. So for later use, let me define the parameter R by this equation, so lambda h divided by square root of MA comma 0 FA. And the ratio of the potential height is given by the R to the fourth power. So R is the ratio of energy scale of the two potentials. Okay? And the total potential is now given by the potential coming from QCD and this time-independent peaky breaking term. So this gray dashed line represents the ordinary potential coming from QCD effects. And here we add the red dashed line. So this is peaky breaking term. Okay. Of course, the size is a bit exaggerated for illustration purposes. And in total, the potential should look like this as the blue line. So the constraint coming from neutral EDM can be expressed on the plane of parameter R, the ratio of the energy scales, and the relative phase theta. And so this gray shaded regions are excluded by neutral EDM. Okay. And as I mentioned, when theta h is very small, say smaller than 10 to minus 10, there is no upper bound on the size of R. And for simplicity here and in the following, I will set the number n equal to 3. So when theta h takes up a special value like pi over 3, the minimum again coincides with each other, and there is no limit on this around this particular value. And also we assume that, so we are interested in the case where the extra peaky breaking terms affect the Qcdxim dynamics. So to this end, we assume that the axiom starts to oscillate first due to the extra peaky breaking term. And this happens in the parameter region above the horizontal line for different values of FA. For instance, if FA is equal to 10 to 12 GB, and if you are above the green horizontal line, the axiom will start to oscillate earlier compared to the conventional scenario because of the extra peaky breaking term. So if we are below this horizontal line, the axiom will start to oscillate due to the ordinary QCD potential. So the dynamics is not affected by the extra peaky breaking term. So this condition was basically, so this equation basically represents what I said. For the extra peaky breaking term to affect the Qcdxim dynamics, the axis should first start oscillate in the potential of the extra peaky breaking. So we assume the temperature at the onset of oscillation in the presence of peaky breaking is larger or higher than the temperature at the onset of oscillations in the conventional scenario. Okay. So we require this condition. Then the dynamics of Qcdxim can be classified, broadly classified into the two cases. One is the smooth shift regime, where the axiom will start to oscillate about the minimum close to the origin. Okay. The second one, which we call the trapping regime, where the axiom will start to oscillate about the minimum which is far away from the origin. Okay. So let me explain what happens in each case. In the first case, the axiom will start about the potential near the origin. Okay. Here denoted by theta h, so it will start to oscillate about theta h when the curvature of the peaky breaking term becomes comparable to the Hubble parameter. But then, as temperature decreases, the potential from QCD grows, so the mass or curvature of the potential increases, and at the same time, potential minimum shifts to the origin. So curvature increases, and also minimum moves toward the origin. Okay. So however, in this process, I mean, when the minimum changes due to the growth of the potential from QCD, the no particle production takes place as long as the curvature of the potential is much higher than the Hubble parameter. So this is known as the adiabatic separation mechanism, which was discussed in detail in the context of cosmological moduli problem. So namely, as long as the oscillation frequency is much higher than the typical time scale of the change of the potential, the axion field simply follows this time-dependent potential minimum and no particle production takes place. So in this case, the final axion abundance is determined by the particle production, which takes place when the curvature of the peak breaking term becomes comparable to the Hubble parameter. And so it means that axion starts to oscillate earlier than usual, then it will be diluted more by the subsequent cosmological expansion. As a result, axion abundance is 1 or 2 orders of magnitude lower than the ordinary scenario. So here, as you can see here, if FA is 10 to 12 GeV, the final abundance is about 1 or 2 orders of magnitude smaller than the usual case. So in this case, the axion abundance is reduced because axions start to oscillate earlier than in the conventional scenario. Something more interesting happens in this second case, which we call trapping regime. So in this case, axion will start to oscillate first around the potential minimum, which is far away from the origin. Okay, so particle production takes place first when the axion starts to oscillate. Then, as temperature decreases, the potential from QCD grows. So this minimum is lifted, so it becomes forced vacuum, but the axion will be trapped there until forced vacuum disappears when the potential from QCD comes to dominate the potential. Then it will start to oscillate about the origin, where the strong phase vanishes, with large amplitude. So roughly speaking, the particle production takes place twice. First, it starts to oscillate, so some amount of axions produced, and the second, the large number of axions produced when this trapping ends. And usually this second particle production dominates over the first one. So in this limit, the final axion abundance is estimated by this equation. And as you can see, there's no dependence on FA or the initial angle. Okay, this can be understood by noting that final oscillation energy is simply determined by the potential height when the forced vacuum disappears, and it doesn't depend on the value of FA. So this equation shows that axion can explain dark matter. So even if FA is very small, say as small as 10 to 8 GeV. In fact, this dependence, this fact itself was first observed in this paper 5 years ago, where we have studied the quality problem of peak symmetry in the context of clockwork axion model. Because as I mentioned earlier, the symmetry breaking scale in the clockwork axion model is much smaller than the decay constant. So if we write down the high dimension operator of peak scalars, its contribution to the axion mass is very much suppressed compared to the usual scenario. So in this context, we have found that the axion abundance is independent of FA. And here we have confirmed this result and also check this numerically in a more general context. So now I show the numerical results. So here in this figure, I show the dependence of axion abundance on initial angle, theta initial, and FA. So in the smooth shift regime, okay, in the middle, sorry, as you can see, the final axion abundance increases as you increase FA. So this is FA equal to 10 to 10th GeV. This is FA equal to 10 to 15th GeV. Of course, compared to the ordinary scenario, the axion abundance itself is 1 or 2 order of magnitude smaller because axions start to oscillate earlier than usual. Sorry, but by the way, in this plot, I took n equals 3, r equal 0.1, and theta h are very small values of theta h. I chose this value because I wanted to allow relatively large value of r. And in the trapping regime, on the other hand, you can see that most of the points are degenerate on the single line. So this is because, as I mentioned, the final axion abundance doesn't depend on the initial angle, and also it is also independent of FA. So here for FA in between 10 to 10th GB and 10 to 14th GB, they generate almost the same amount of axion dark matter in this regime. However, the abundance itself exceeds observed abundance. So you need to explain dark matter density, you need to weaken the trapping effect to some extent. And this is shown in this plot where we reduce the value of R so that the trapping effect becomes weaker, so that the degeneracy is a bit lifted in the trapping regime, as you can see here, but still FA equal to 10 to 11th GeV or 10 to 10th GeV gives almost the same result in this trapping regime. So the axial abundance is indeed independent of FA and the initial angle, and it can explain all dark matter for this choice of parameters. So here, because of the numerical cost, we studied only down to 10 to 10th GeV, but we believe that we would obtain the same result for FA as low as 10 to 8th GeV. So in the previous plot, we fixed R and theta H and varied theta initial and also changed the FA. But here I show the contours of the axial abundance on the plane of R, the size of PQ breaking, and theta H, the relative phase of the PQ breaking with respect to the potential of QCD. So the left panel is for FA equal to 10 to 12 GeV. The right panel corresponds to FA equal to 10 to 13th GeV. The gray shaded regions are excluded by Newtonian. And so in the case of FA equal to 10 to 12 GeV, when R is very small, the effect of peak breaking, extra peak breaking is negligibly small. So the axial abundance is constant in this range. Say for R below 0.01, the axial abundance is constant and it's close to the observed abundance. But if you turn on the peak breaking, extra peak breaking, the abundance of R, abundance of axiom decreases as you increase R. And again, this is because the early onset of oscillations. And so this is the same for 10 to 13 GeV. As you can see, when the extra peak breaking is negligibly small, nothing happens. But as you turn on extra peak breaking, abundance decreases. At certain point, you can explain dark matter abundance. Of course, to explain dark matter abundance in this scenario, you need to fine-tune the relative phase about 10 to -9 or so. So from phenomenological point of view, this scenario itself is not so appealing, but anyway, you can reduce the abundance by tuning out the extra peak breaking. The situation is more interesting in the case of a trapping regime. So here we set FA equal to 10 to 11th GeV in this left panel and 10 to 10th GeV in the right panel. Okay, and then these gray shaded regions are excluded by Newtonian, and the axial abundance is very small, much smaller than dark matter density. When R, the size of peak breaking is very small and it's constant around here, it's equal to 0.03. In the case of 10 to 10th GeV, its abundance is even smaller, 0.003. But once you turn on the extra peak breaking, the abundance starts to increase significantly. And you can explain all dark matter on this red line. And as you can see, you can explain all dark matter for almost the same value of R. Okay. And it doesn't depend on values FA, as I mentioned. So also you can see that the other contours agree with each other. If you compare the left panel and the right panel, the same abundance is realized for the same value of R. Okay. So this is due to the trapping effect. Okay, in the remaining time, probably 10 minutes or so, I will explain the ice curvature perturbations. So far, we focused on axiom abundance, but we are also interested in axiom ice curvature perturbation, because here we are assuming the pre-inflation scenario where the peak symmetry is already broken during inflation and is never restored afterwards. In this case, axiom acquires quantum fluctuation during inflation, which leads to the ice curvature perturbation. The size of ice curvature perturbation is determined by the axiom, the fluctuation, and which is over the hyperparameter during inflation. And in terms of fluctuation of angle, it is the rate given by the ratio of the hyperparameter and the decay constant. And because the initial oscillation amplitude is different from point to point in space, the final axial abundance also is different from point to point, and this fluctuation is independent of the adiabatic perturbations. So, and this gives that this exhibit itself in a different way in the CMB perturbation, CMB power spectrum. So, the small mixture of ice curvature perturbation is only allowed. And so we have a very tight upper bound on the ice curvature perturbation from Planck. And this ice curvature perturbation is given by a function of dependence of the axial abundance on initial angle times the fluctuation of initial angle delta theta. Okay. And in the smooth shift regime, so in the first case where the axial start oscillating about potential close to the origin, the situation is relatively similar to the conventional case. And axial abundance, in this case, if you neglect the harmonic effect, the final axial abundance is proportional to the initial misalignment angle squared. So this part, okay, the dependence of the axial abundance on the initial angle is simply proportional to 1 over initial angle. So the final ice curvature perturbation is simply given by the ratio of the hyperparameter and initial axial feed value. Okay, theta times Fa is nothing but axial feed value. So this expression itself is same as in the conventional case, but in our case with extra peak breaking, the axial starts oscillate earlier, so the abundance is reduced. So to explain dark matter density, the required value of Fa is a bit larger compared to the conventional scenario. So the denominator is larger. The ice curvature perturbation gets suppressed. In this case, so the constraint on the hyperparameter is relaxed in this case. On the other hand, in the trapping regime, as I mentioned, the final axial abundance becomes insensitive to the initial angle. So this part is suppressed in the trapping regime. So the ice curvature perturbation gets significantly suppressed in the trapping regime. So anyway, in most cases, the actual ice curvature perturbation gets relaxed. So this figure shows the ice curvature bound on the hyperparameter in the first case, namely the smooth shift regime. And these dots are numerical results, and these lines represent the analytical estimate taking account of the harmonic effect. These red points and the purple dotted line corresponds to the conventional case. So as I mentioned earlier, the bound on the hyperparameter is somewhere between 10 to 7 GB or 10 to 8 GB for Fa between 10 to 12 GB and 14 GB or so. But now if you turn on the extra peak breaking, the bound becomes this green line or blue solid line, depending on the size of extra peak breaking. And you can see that the ice curvature bound on hyperparameter is relaxed by this amount. This ice curvature bound becomes very tight for FA below 10 to 13 GB, and this is due to the harmonic effect. Because abundance is reduced in this scenario, in order to explain dark matter density, you would need a harmonic effect for already for FA near 10 to 13 GB or so. On the other hand, in the trapping regime, the effect is more significant. So again, these points represent a numerical result, and these two lines represent analytical result. And you can see that the in the conventional scenario, ice curvature perturbation gets very tight as you go to small FA due to the harmonic effect. But in our scenario with extra peak breaking, because the final Axiom abundance is less sensitive to the initial angle, so the ice curvature perturbation is pretty much suppressed compared to the conventional scenario. So the upper bound on the hyperparameter is around 10 to 7 GB for a wide range of the axion decay constant. Okay. And as you can see, so depending on the initial feed value, theta initial, so the numerical result is shows some strange behavior, and we believe the numerical result itself is correct, but the reason why the result kind of scattered or depends on the precise value of theta initial, and it also depends on FA in a strange way, is that, as I said, in this case, the axiom abundance becomes less sensitive to the initial feed value, but at the same time, its dependence becomes very complicated in this case, because in the trapping regime, I said the production can be the production takes place twice. The first is starts oscillate around the peak breaking term, and the second when it's the trapping is over, and that takes place when the force vacuum disappears. But precisely speaking, you cannot completely separate the two dynamics, and especially the axion dynamics when the force vacuum disappears is very important, and axion may be moving toward the positive values or negative values, and that kind of the motion affects the final abundance, and also the potential when the force vacuum disappears is significantly deviated from the simple product potential, and also it's time dependent. So the final abundance is not sensitive to the choice of initial angle, but the dependence itself becomes very complicated, and we can still make an order of magnitude estimate that is shown by this blue line, but it's very hard to estimate ice curvature perturbation analytically to explain those numerical results. But we can see that overall agreement between the numerical results and the analytical results. Okay, so let me wrap up my talk. We studied the effect of extra peak breaking term motivated by the fact that the global Riemann symmetry is probably broken expressly based on the argument of quantum gravity. And we have found that in the presence of such extra peak breaking term, the axiom abundance can be either reduced or significantly enhanced, depending on the initial position. And in particular, the axiom can explain all dark matter density, even if FA is as small as 10 to 8 GB, close to the lower end of the axiom decay axiom window. And this is due to the enhancement of, so this enhancement is due to the trapping phenomena. The axiom will be trapped in the force vacuum until force vacuum disappears completely. And we also found that axial curvature perturbation is also suppressed. So this scenario provides a new production mechanism, especially for the axiom mass, much heavier than micro electron volt. Okay, that's all I have to say. Thank you very much for your attention.
Thanks a lot. Now the session is for discussion or questions. Do you have any questions or comments?
Can I ask a question on the trapping regime?
Yes, please.
So in the trapping case, is it possible to have barrier when you turn on QCD potential and delaying the oscillation time scale? Or is always case that you have immediate kind of classical rolling the scalar field as soon as you turn on the QCD potential?
Well, first of all, when you are in this, by the way, can you see my screen?
Yes.
Yes.
Okay, so as long as you are in this white region, there is no force vacuum in the low energy. And so there is barrier, but that disappears at a certain point. And only if you are in this range, R greater than 1 or so, then force vacuum remains in the current universe. And depending on initial angle, it may be trapped there. But we haven't done this very much.
But even in this trapping region, in the end, I mean, at some point, it turns toward a true minimum and start oscillating because of the classical rolling, right? I don't know if
I believe so, but I'm not sure. Well, I haven't studied.
Okay.
Yeah, we focused on the case where the force vacuum disappears at the end of the day.
Okay, I see.
Yeah, you may have successful cosmology in that case too, so it's worth studying.
I see.
So Fumi, can you explain how you can obtain the PQ breaking potential? I mean, how general it can be? You use a particular form of the potential, yeah.
Yeah, the easiest way to get to this potential is to couple the axiom to the hidden non-regular symmetry. And when the hidden gluons get joined, there's potential like this. Or you can also consider high PQ scale is to the then with kind of potential for the axiom.
Okay, thanks.
That's it.
Yeah, good.
Can I ask can I ask a short question? So here you ignored, you introduced PQ breaking term, but maybe it is originated from some higher dimensional operator. And recently people talk about axion kination, the importance of the axion kinetic term for the axion abundance. I don't know if you have a different mechanisms, the effect of the PQ breaking term on the axion abundance. And I don't know, have you thought about which one is the dominant axion kination or this time-independent PQ breaking effect? These two might be comparable or some.
Here we just consider the potential from QCD and time-independent PQ breaking, and so the kind of kinetic misalignment mechanism doesn't apply to this setup. But the similar thing, the phenomena similar to the kinetic misalignment have been considered in the context of Axiom in the past. For instance, in those papers shown here, they add the kind of high dimension operator, and if PQ scalar takes a very large wave in our universe, effectively this gives a large mass to the axiom can be kicked. And by considering heavy axiom as people discussed the suppression of ice curvature perturbation or applying to the spontaneous baryogenesis almost 20 years ago. So much before.
Yes, I see. Yes, I see. It's old idea. I see.
Yeah, because of the time limit, let's stop here. Let's thank Fumi again. Thank you.
Thank you very much.
Thank you.
So let's invite the next speaker. Wen-Yin, can you share your screen?
Yeah, sure. Maybe I can do this. And so can you see my screen?
Yes, I can see your screen.
And yeah, can you see my pointer?
Yes.
Oh, great.
Okay, so our next speaker is Wen-Yin, and he will talk on axionic unification of inflation and dark matter. Can you start now?
Yeah, sure. Thank you very much. And thank you very much for the invitation. So I will talk about the unification of inflaton and dark matter by an axion-like particle. So this talk is mainly based on the two papers in collaboration with Ryuji and Fumi, who is the previous speaker. And also I will talk about a little bit on our ongoing project on this topic. Okay, let me begin. So as you know from several nice talks, the success of the lambda CDM model relies on the two unknown degrees of freedom that are inflaton and dark matter. Interestingly, they are similar. So you know, to derive inflation, inflaton needs to have a potential with a flat direction. This flat direction should not spoiled by Coleman-Weinberg correction. This implies that the inflaton seems to be a neutral field. After the inflation, the inflaton starts to oscillate around potential minimum, and the coherent oscillating energy dominates the universe once. Later, it decays into the small particle to reheat the universe. During the slow law, there is quantum fluctuation of the inflaton field, and later this quantum fluctuation becomes the the density perturbation of the coherent oscillation of the inflaton. Then this becomes the primordial density perturbation of the hot plasma, including the photons, including the baryons. On the other hand, dark matter is also neutral, and it is cold and long-lived. Interestingly, now we know that the Ice Curvature mode on the dark matter is suppressed. This implies that the density fluctuation of the dark matter looks somehow similar to that of the photons and baryons, which originate from the perturbation of the inflaton condensate. So inflaton and dark matter look similar. They are both neutral, once dominated early universe, and perhaps have a similar density fluctuation. The difference is that the inflaton decays, but the dark matter does not decay. So the question is whether the inflaton is the dark matter. If it is, then we can also explain the origin of the abundance of dark matter. It can be the remnant of the incomplete reheating. So the reheating, if the reheating due to the inflaton decay is incomplete, then some of the inflaton remains, and a fraction of the inflaton condensate just becomes the dark matter. So I think this is a simple possibility. If we consider this simple possibility, we have to answer a question: is that why the inflaton is long-lived in the present vacuum? There are several possibilities that have been considered. For instance, we can consider these stabilities due to the symmetry in the present vacuum, like the case of the WIMP scenario. So inflaton is the lightest charged particle in the present vacuum, but in the early universe, due to the large expectation value, the symmetry is effectively broken, so we can have the heating. More recently, some authors, including our organizer Fumi and Kimiko, have proposed propose that this symmetry can be approximated to quantum gravity effect, then the resulting parameter region will be quite different from the exact symmetric case. But today, I would like to focus on another possibility for the longevity of the inflaton. That is through low condition in axion inflation. This is what I will be talking about. I will show in a large class of axion inflation models, the inflaton can be the dark matter whose stability is due to the through low condition. By coupling this inflaton to photon, we will find that the reheating can be successful with remnant of the dark matter. The dark matter abundance can be explained if the inflaton mass is around 0.01 electron to 1 electron volt, and photon coupling is around 10 to minus 11 GeV inverse. Interestingly, this region has a significant overlap with the future sensitivity reach of the axion helioscope Yakuzo test, and also this region is hinted in various astrophysics phenomena like the horizontal branch star cooling. And in the end, I will also comment on our ongoing study about the coupling the ARP to gluon, and then I will show that prediction on the strong CP phase is smaller than 10 to minus 9. Okay, let's begin the main part. So I would like to talk about axion inflation. The reason I like axion inflation because the through low flat direction it becomes stable under radiative correction. This is due to the discrete shift symmetry of the axiom. Thanks to this discrete shift symmetry, the potential of the axion or inflaton becomes periodic. Then we can expand the potential in Fourier series. There are several realizations of axion inflation. The famous one may be the natural inflation. In this case, the potential is composed of single cosine term. Now it is known that if we want to fit the CMB data, we will see that the decay constant for this axion will be super Planckian, and the field excursion is also super Planckian. So there may be some issue on quantum gravity. And moreover, recently, this model is unfortunately excluded due to the too high scale inflation. Therefore, we are led to consider the axion potential with 2 or more cosine terms. In this case, the model is called multi-natural inflation. In multi-natural inflation, the CMB data can be well explained with sub-Planckian decay constant, sub-Planckian field excursion. For simplicity, let's consider the potential composed of 2 cosine terms. In the addition, with the additional cosine term, we have additional 3 parameters. So this lambda is the inflation scale. This theta is the relative phase between the 2 cosine terms. You know, we can always redefine the field to absorb a phase in one of the cosine. So this is the generic phase in this setup. And here, kappa is the relative height between the 2 cosine terms. And we also have an integer characterizing the second cosine term. In fact, the scenario or the inflaton mass highly depend on the parity of this n. Today, I would like to focus on the case this n is odd, and this assumption is quite important in deriving the conclusion of today's talk. So we will consider odd n. Now let's consider this kappa relative height is around 1, relative phase is around 0. Then we can find this potential, inflaton potential has this kind of shape, which includes a flat hilltop. So we can derive hilltop inflation. In the extreme limit, the kappa equal 1, theta equal 0, we will find that in the hilltop or in the origin of the field space, we have a dominant quartic term. So this inflation model is similar to the quartic hilltop inflation. Then we can take use of the knowledge of the quartic hilltop inflation. From the CMB normalization, we can find that the quartic coupling becomes around 10 to minus 12. In one scenario, this CMB normalization condition fix the ratio of the inflation scale to the decay constant, which is around 10 to minus 3 also. It is also known that in the quartic hilltop inflation, the spectral index is difficult to explain when the inflation scale is not very high. In one scenario, we can include a non-vanishing but tiny relative phase. Then this relative phase contributes to a linear term in the potential. This linear term slightly shift the horizon exit value of the inflaton field. Then we can slightly change the curvature at the horizon exit, which enhances the spectral index. Then we can get the better fit of the CMB data. Once we include this linear term, then the hilltop of the potential gets some curvature. The typical size of curvature is the typical scale of the inflation, which is the Hubble parameter. In the axion hilltop inflation with odd end, we have a nice feature that is upside down symmetry. We can flip the potential, and we can find the potential shape does not change by the flipping. This feature means that the shape of the hilltop is same as the shape of the vacuum. So the CMB data is a measurement of the inflaton particle property in the vacuum. For instance, the CMB normalization sets the self-coupling of the inflaton field in the vacuum to be around 10 to minus 12. The curvature at the hilltop means the mass of the inflaton in the vacuum is around the Hubble parameter. When we search those equations, we can obtain the acute relation between the inflaton mass and the decay constant like this. So mass is 10 to minus 6 times the decay constant square divided by m Planck. So this is a prediction of our scenario. By coupling the axion to photon, then we can call this axion-like particle or ARP. Then we can find the parameter region of this scenario like this. So the horizontal axis is the mass of the ARP. The vertical axis is the photon coupling. The colored range are excluded due to various bounds from the astrophysics and the CMB observation. The red solid line corresponds to the case the anomaly coefficient of to the photon is 1 and 0.1. If we consider this C gamma equal or the 1 is natural, then the successful inflation predicts the parameter region around here. So we can see that there is a region that allowed by the various astrophysics and CMB bounds. This region has the ARP of sub-electron volt or electron volt scale mass. In this region, the ARP can be the successful dark matter candidate because the lifetime is much longer than the age of the universe. Now the ARP coupled to photon, then we can discuss the reheating. As I said, that the ARP is long-lived in the vacuum, but it is short-lived in the early universe. This is because of the sizable self-coupling and the large amplitude soon after the inflation. Soon after the inflation, the inflaton start to oscillate around the potential minimum with an amplitude around the decay constant. So this is around 10 to 7 GeV. Then by combining the self-coupling value, we can see that the effective mass soon after the inflation is around 10 GeV, which is 10 orders of the magnitude larger than the vacuum mass, which is around electron volt. Therefore, the decay rate soon after the inflation is around 30 orders of magnitude larger than that in the vacuum. So the decay soon after inflation is very efficient. In fact, the decay is too efficient. It produces too much thermal plasma. Soon the temperature grows to be comparable to the effective mass. Then the thermal blocking becomes important. Afterwards, the reheating proceeds via the scattering effect rather than the perturbative decay. By including the decay process and the dissipation process, we have solved the Boltzmann equation to estimate the efficiency of the reheating. And we found that in the successful region, the reheating is instantaneous. So soon after the inflation reheating complete. But it is not completely complete. There is some remnant of the ALP condensate. This is because both the decay rate and dissipation rate depends on the amplitude of the inflaton. If we take this amplitude to be close to zero, then the decay rate and dissipation rate will be close to zero. So we must have some amount of the ALP remains after the reheating. By solving the Boltzmann equation, we have also checked the abundance of the remnant ALP condensate. By imposing the remnant abundance to be the observed dark matter abundance, we get the parameter region like this. So we can see that there are colored data points. Those colored data points correspond to have the natural charge assignment, the anomaly coefficient value. So basically, this is a natural range. We can see that this natural region explaining the dark matter abundance is consistent with the cast band or horizontal branch star bound. We have to be more careful in the case that the reheating succeeds via the dissipation effect, because dissipation effect has a diagram or scattering process has a diagram like this, but we also have a similar diagram to produce the ALP. So this is basically the thermal production of the axiom. Then we also have the production of the hot dark matter. So basically, our dark matter has two components of the momenta. One is the cold component, which is from the remnant of the ALP condensate. The other is the hot component from the thermal production. So this hot component's ALP can be characterized by the effective neutrino number, which turns out to be 0.03. This hot component of the ALP cannot be too abundant, because otherwise the dark matter will free stream. So we have to impose the hot dark matter bound, which is around 1 electron volt. So but it excludes the mass range above this figure. So we can see that the successful inflation and the abundance and the hot dark matter bounds points to this region. In addition, there is also bound from late forming dark matter, which I didn't discuss in today's talk, but basically we need to have the condensate transition between from the radiation-like oscillation to the matter-like oscillation early enough. This set a bound around the 0.001 electron volt or 0.01 electron volt. So we can see that several independent conditions point to this region, and we have allowed the region. So we consider this coincidence quite non-trivial, so we call this scenario ALP miracle. In the right figure, the ALP miracle region is around here. We can see that the parameter region has a significant overlap with the sensitivity reach of the future axion helioscope YACZO. So most of the parameter region can be tested in the future. In addition, since our scenario predicts the dark radiation around 0.03, this can be also proved in the future CMB and the BL experiments. Moreover, this region has overlap with the cooling hint of the horizontal branch star, and also it was discussed that the 1 electron volt ALP can, with this kind of coupling, can give a better fit of the extragalactic background light analysis. So actually, this is the main message of today's talk. from now I will explain, I will comment on our ongoing study. So if you look into this figure, we can see another coincidence. That is the coincidence between the Qcdxim region and the ALP miracle region. So the question is whether this ALP is relevant to the strong CP problem. Naively, there is tension, because if we want to have this ALP to be relevant to the strong CP problem, then we have to couple this up to gluon. Then we have the bounds from supernova and the neutron star cooling, which set the decay constant to be greater than 10 to 8 or 10 to 9 GeV. On the other hand, the ALP miracle region says the decay constant is around 10 to 7 GeV, so they have a tension. But let's take the coincidence seriously. Let's consider whether the ALP can, what is the consequence that ALP couple to gluon. There are two possibilities that ALP can couple to gluon. One is that the astrophysics bound is not so rigorous, so maybe it is allowed. The second possibility is that the ALP can have some light quark coupling. Then for certain coupling, the axiom nucleon coupling can be suppressed. This is the so-called nucleophobic axiom or hydrophobic axiom. I will not explain in detail, but the essence is that we can, for certain coupling to light quark, we can make this ALP isosinglet. Then ALP pyomixing is suppressed. For instance, we can take this CU is 2/3 and CD is 1/3. Then this condition is approximately satisfied. Then we can see that the nucleon coupling and the proton coupling are suppressed to be order 1%. Then the supernova and the neutron star cooling bounds by using the central value are relaxed to be around 10 to 7 GeV. So then the ALP miracle region can be consistent with the supernova and the neutron star bounds. So let's consider this possibility. Then we need to include the QCD instanton contribution to the potential. This contribution breaks the upside down symmetry, which is given like this. Still, we can have successful inflation in addition to the 2 cosine term potential V-inf with this contribution. This is because we can, in the expansion, in the Taylor series expansion around the hilltop, we can always make a parameter redefinition like this. So then the successful inflation region is kept intact. But then, this breaks the upside down symmetry. This breaking corrects ALP mass in the vacuum. Interesting thing is that when we take this theta QCD, which is the phase in the QCD sector to be 0, the prediction in the ALP miracle, the mass Hubble parameter relation doesn't change. This is because of the coincidence of the regions of the Qcdxim and the ALP miracle. This potential at the most contribute to the ALP mass by the order of the Qcdxim mass with fixed decay constant. On the other hand, this Qcdxim mass is comparable to the ALP miracle prediction. Therefore, it at most corrects the relation by an order 1 factor. However, when this theta QCD is not that small, then the correction becomes larger. This is because we will have a upside down breaking linear term in the vacuum. Then this contribution shifts the infraton vacuum away from the upside down related position. Then due to the large shape coupling, the curvature is generated. So you can see that with large theta QCD, we will get a larger mass of the infraton in the vacuum. We cannot have too large mass to have or scenario consistent with dark matter. In particular, the hot dark matter bound sets the exclude the region the mass is greater than order 1 electron volt. This implies that the strong CP phase in our scenario is predicted to be below 10 to minus 9. So in other words, if we require the ARP couple to gluon, and if we require this ARP is consistent with the dark matter and inflaton, then the resulting the strong CP phase is smaller than 10 to minus 9. So this is the end of my talk. So I show that in a class of ARP inflation models, the ARP inflaton can be the dark matter. In this case, the stability is due to the slow condition via the upside down symmetry. We can have successful reheating of the via the photon coupling due to the decay and the dissipation effect. The reheating is not complete because it depends on the amplitude of the inflaton oscillation. In the end, some of the dark matter remains to contribute to the cold dark matter. The resulting parameter region is like this, which can be tested in the future and hinted by horizontal branch star cooling. If this ARP is coupled to gluon, then by requiring the inflaton and the successful inflation and the dark matter, we obtain that the strong CP phase is suppressed. Thank you very much.
Thank you very much for the nice talk. So now the session is for the discussion and questions. Is there any questions or comments from the audience? Okay, so you pin down the mass and of photon-photon coupling to successful inflation and also reheating. And you mentioned the HB cooling effect, right? So could you explain a little bit more? How can it be detected?
So prediction of the scenario has a mass around here and the photon coupling like here. So this is a region of the, so it is dark matter, but it is also a particle with this kind of coupling. So it can be produced from the sun. Then from the axion photon conversion, we can detect this axiom by in the solar axion helioscope. So most of the region around here can be proved by looking at the sun. Also, during the reheating, there is thermal production of the axion like particle. This is not condensate but particle. So it contributes to the dark radiation. So in the future, we can also prove the from the CMB and BAO experiment to prove the dark radiation. So I think those two are a good channel to
how about supernova cooling? Is there any?
In the original, the ARP miracle scenario, we only consider this ARP coupled to photon. So in this case, there is no constraint from the supernova. But if we couple this to gluon, we need to be careful because supernova is very it have a stringent bound. So therefore, we need to consider a specific coupling to the light quark. In this case, we can have a certain cancellation of the nucleon coupling and the neutron coupling and the photon coupling. Then we can relax the bound to be 10 to 7 GeV.
Okay.
In this case, it can be consistent with the supernova, and perhaps it can be proved in the future supernova.
Yeah, Kimiko, do you have a question?
Yes. axion condensate becomes the cold dark matter, and the quantum part becomes the hot dark matter. Is it possible that the quantum part of axion can be a warm dark matter to solve the, for example, core-cusp problem? To become warm dark matter.
For warm, the mass range is slightly smaller. It is. If we want to explain, so you can see that this is the relation between the. So if we want to have the successful reheating, then the mass is around here. So if we want to. No, in any case, I think it will be too warm. So we produce this dark matter. As the hot component is completely thermalized. So I think it even if we increase the mass to explain the dark matter abundance, then it cannot be the dominant dark matter. So I'm not sure whether I guess it will affect in some how to say the boundary region for the exclusion. It would affect some small scale structure, and there is some relevant study to discuss the small scale structure issue, but I'm not sure whether it is very. Yeah, there is a possibility, but I'm not sure whether. I didn't perform the analysis. I should say. Yeah.
Okay, we may discuss it further later on. Okay, let's thank our speaker once more. Thank you.
Thank you.
Now let's invite the next speaker, Matthias.
Hey, Matthias.
Hi, can you hear me?
Yes, I can hear you. Can you share your screen?
Yes.
I'm sorry for being too early, Matthias. 7 a.m.
No worries, no worries. That's fine. Can you see my screen?
Yes.
All right.
Okay.
Let me put it full screen. It should work.
Right, it works fine. All right, the next speaker is Matthias Pierre from DESY, and he's going to talk on out of equilibrium dark matter. So Matthias, please.
Perfect. Well, thanks a lot to the organizers to give me the opportunity to talk today. So I would like to talk about out of equilibrium dark matter, and in particular to talk about production and possible cosmological signatures. So the starting point of my talk is essentially the following. This is the plot that I'm sure that all of you saw probably 10,000 times, which shows the dark matter nucleon scattering cross-section as a function of the dark matter mass. And all these different lines correspond to current constraints from direct detection experiments. So thanks to our experimental colleagues, the bounds are now reaching the value of around 10 to the minus 46 centimeters square for the cross-section for dark matter mass of order 100 GeV. So thanks to these very nice results, well, we know that the most simplest WIM scenarios have been essentially pushed towards very small corners of the parameter space. And this actually led the theoretical physics community to start lacking of interest on weakly interactive massive particles, as you can see on this histogram on the left, or you can see the number of occurrences for the WIMP world essentially decrease since 2016. On the other hand, interest in alternative scenarios, such as the freezing mechanism, has essentially risen since a couple of years. So in this kind of alternative scenarios, the dark matter coupling to the standard model particles is essentially much weaker than for the WIMPs, and typically the signatures are also less important. So this is actually something that I would like to address today. And to look at what are the cosmological signatures of this kind of out of equilibrium dark matter candidates, and is it possible to actually probe the dark matter production mechanism? So I would like to base my talk essentially on this paper that appeared last year on the archive in collaboration with Guillermo Ballesteros and Marcos Garcia. So how to produce essentially out of equilibrium dark matter? Well, Let me just remind you essentially a naive picture of the early universe dynamics. So inflation can be achieved while a scalar field is slowly rolling down its potential here, as you can see on this plot. And eventually we know that the inflaton has to reach the minimum of its potential, start to oscillate around, and eventually produce standard model particles. So in the following, I will just assume that the production of standard model particles occurs via a perturbative decay of the inflaton. Based on this simple picture, there are actually a couple of possibilities of producing dark matter in a state of equilibrium. The first one is the production of dark matter particles via the so-called ultraviolet freezing, which consists in annihilation of standard model particles into dark matter particles. And in the following, I will just assume that the cross-section for this kind of process will eventually scale as a power of the center of mass energy S with some index n and normalized by some scale. And in the case essentially where this index n is positive, the cross-section is sensitive to the highest temperature of the universe, and dark matter particles are produced in the hottest moment of the universe. So this is why we talk about ultraviolet freezing. There are actually other possibilities of producing dark matter in this case. Since we assume that the standard model particles are produced by the decay of the inflaton, dark matter could also be as well produced in the same way. And alternatively, I will consider the possibility for dark matter to be produced via a decay chain. So for example, some particle decaying to this particle that I call A and subsequently decaying to dark matter particles. So a common point about all these scenarios is that dark matter is essentially produced in the very early stage of the universe. And essentially, the only thing that this dark matter particle does until now is to interact with the standard model particles, but only gravitational. However, there is a slight difference in all these scenarios is essentially the kinematics and how these particles are being produced. And what is important is that the kinematics is imprinted in what is called the dark matter phase space distribution, which is the quantity that I would like to talk about now. So the dark matter phase space distribution is essentially this quantity that allows to estimate all the quantities relevant for cosmology, such as number density or energy density, which can be expressed as a function of integrals of this quantity. In order to determine this phase space distribution, we can essentially solve the Boltzmann equation, which relates the time derivative of the phase space distribution to the Hubble expansion rate. And on the right-hand side, we have the so-called collision term, which accounts for all the interaction processes that can affect the phase space distribution for these dark matter particles. So once I manage to determine the collision term, I can essentially solve this equation by integrating the collision term over time. And the only big subtlety that I need to take into account is the redshift between the time at which these dark matter particles are being produced and the time at which I'm going to evaluate the phase space distribution. Sorry. So essentially, in all these scenarios that I mentioned, dark matter production will occur at a very high energy scale, but eventually production will stop. And so after this decoupling, the distribution function can be only expressed in terms of what is called the co-moving momentum, which is the dark matter momentum times the scale factor and normalized by some scale that I call T star here. This allows, for example, to factorize out the time dependence for the number density. As you can see here, an explicit dependence on the scale factor to the power -3. And essentially, this function here encodes the momentum part of the distribution function. So just to give you an idea about how to compute these things, I'm taking just the example of the case where dark matter is produced by the decay of the inflaton. So let's assume just an inflaton sitting at rest in the bottom of its potential and decaying, for example, to a dark matter pair or a photon pair. In this case, the collision terms takes a quite intuitive form. It's something which is proportional to the inflaton decay rate, the branching fraction to the outgoing particles, inflaton number density, and there is this delta distribution that essentially ensures that the outgoing particle carries a momentum which is half of the inflaton mass. So once I know my collision term, I can integrate it in the way that I just described before. And unfortunately, this is typically non-analytical, so I need to compute it numerically for a specific case. But if I look at essentially the very early time, so when the time is much smaller than the reaching time, I can approximate the distribution function as being something like which goes as the momentum to the power minus 3/2, and you can see this sharp theta cutoff here, right? But in practice, I need to solve all of this numerically, and this is essentially what I got here. As you can see, we can actually factor out, we can re-express, the phase space distribution in terms of all these factors here. What is important is the momentum dependence of the distribution, which is encoded in this function that I call FR, which is actually represented in this plot. And you can see that this function is peaked around Q order 1, and Q order 1 actually means a temperature close to the reaching temperature. It's essentially when the decay of the inflaton is the most efficient. And as you can see, this function can be essentially well approximated by something which goes as a power law, minus 3/2. So we recover the power law from the example before, and an exponential decay tail. And once I computed my phase space distribution, I can essentially express all the quantities relevant for cosmology, such as energy density, here in terms of very few parameters, such as the branching fraction of inflaton going to dark matter particles, the dark matter mass, the reaching temperature, and the inflaton mass in this case. So the second case I mentioned is the ultraviolet freezing via scattering. So annihilation of standard particles going to dark matter pair. So at this stage, you could wonder, are there actually any particle physics scenario in this context where this can actually be achieved? Well, let me just give you a couple of examples. So I just remind you how we parameterize the cross-section in terms of the power of the center of mass energy. So yeah, there are actually a couple of examples. For example, if the dark matter is secluded from the standard particles via some via the exchange, for example, of a very massive gauge boson, you would expect the cross-section to go as the center of mass energy divided by the mass of this particle to the power 4. I would like to actually highlight a case which is probably the most interesting one to me, which is the so-called gravity-mediated freezing case. Because there are only very few things we know about dark matter, but one thing which actually comes from by assumption is that dark matter must be coupled to the standard particles via at least gravity. And in this case, you can actually mediate dark matter production via annihilation of standard model particles mediated by the graviton here. This is represented in this diagram. And in this case, you would expect the cross-section to scale as something divided by the Planck mass to the 4. And in this case, actually, you could actually produce all the dark matter only via gravitational interaction. And this is something very interesting because you cannot get rid of this contribution, because by assumption, you have actually a coupling between your dark matter particles and the standard model particles. And of course, well, there are actually a couple of other possibilities of producing dark matter in this context, and in particular in the context of modified gravity. So I give you here a couple of references, but of course, there are still many more. All right, so essentially, we did the same exercise in this case of computing the phase space distribution in the ultraviolet freezing by scattering case. And we can, same thing, we can rewrite the phase space distribution in terms of all these parameters and this function that carries the momentum distribution of this quantity. And in this case, the quantity T star can be essentially identified to the photon temperature at the present time, rescaled by some factor of entropic degrees of freedom. What I wanted to show you here on this plot are the various momentum dependence for all these cases, depending on the index of dependence of the cross-section. And we wanted actually to look at what is important of the statistic of the initial state particles. So whether it's we are considering bosonic states or fermionic states, and you could see that there is a slight difference in all these cases, but essentially all distribution looks essentially very peaked at some point and decay as an exponential later on. What we have also found is that if you assume Maxwell-Boltzmann distribution for the initial state particles, it essentially looks like you're looking at the scattering between a fermion and actually a boson. So in all these cases, the phase space distribution looks actually different from a thermal distribution, but can be well fitted with this relatively simple formula, which is something which goes as a power law and then decays as an exponential. So now if you consider an index n which is even larger, n equals 6, for example, your cross-section dependence on the center of mass energy becomes so important that you you're starting to become very sensitive to the highest temperature achieved in the universe, which can be larger than the reaching temperature. And this is actually represented in this plot, which shows actually two sets of curves, one for Tmax over T rating equal 50 and here for 10. And you can see that there is a strong dependence on this parameter Tmax. And you can see that the phase space distribution looks slightly more complicated in this case, because it cannot just be approximated by a power law and then decreasing as an exponential. There is still an imprint of essentially what happened before reading in the dark matter phase space distribution. And this is something that we are very interested about. Another possibility that I would like to mention, so in all what I said previously about ultraviolet freezing via scattering, I assume that the standard model photons are essentially thermalized in the universe and then dark matter can be produced out of it. But there is a stage slightly after inflation when the scalar field reaches the minimum of its potential and starts producing standard model particles, where these actually produced particles do not have enough time essentially to actually thermalize, but could still produce dark matter particles. So this is what I call a non-thermal population of standard model particles. And this particle could produce also dark matter. And in this case, the resulting dark matter phase space distribution will differ from what we would expect from a thermal standard model particle distribution. So we did the same exercise of computing the phase space distribution. And even though this process is highly non-thermal, the phase space distribution looks like something which goes as a power law. So you recognize this power minus 3/2, which is inherited from the non-thermal distribution of the parents, and then an exponential decrease. All right, and the last case I would like to discuss today is the possibility of producing dark matter via decay chains, so inflaton decaying to something, and this something decaying to dark matter eventually. And what is actually interesting in this case, I'm just showing you a very qualitative plot, is that depending on the moment at which this intermediate state particle decays to dark matter, you would expect a very different dark matter phase space distribution. By this, I mean, if this intermediate state particle decays while being relativistic or not, you would expect a very different distribution. And this is represented in these two plots, where on the left-hand side, you can see the distribution in the case where this intermediate particle decays while being relativistic, and on the right-hand side, while being non-relativistic. So on the left-hand side, you get essentially something which goes as a power law and then exponential decays. And on the right-hand side, you get essentially a phase space distribution that looks like roughly a triangular shape. So it's actually quite interesting to see how this phase space distribution could be so different, even though they are both generated by the same kinematic process. All right, so this is just a snapshot to summarize essentially all the possible phase space distribution that you would expect in the cases that I've discussed, and representing more or less when these dark matter particles are being produced. So as you can see, all the distribution are different, and the question is, what is actually the cosmological imprint of all these kind of scenarios, and is it actually possible to disentangle them? So this is the second part of my talk, and I would like to talk about aspect related to cosmology. Right, so as I said before, essentially the cosmological role of atomic dark matter can be encapsulated via all these quantities that are relevant for cosmology, such as the background energy density and background pressure that can be expressed in terms of integral of this dark matter phase space distribution. I'll just remind you here how we define this comoving momentum as being the momentum times scale factor divided by this scale T star that I just used for convenience. Essentially, once I know my phase space distribution, I can compute both energy density and pressure and compute the equation of state parameter, which is just a ratio of these two quantities. What is interesting here is that in pure lambda CDM framework, we know that the equation of state parameter of the dark matter must be precisely 0, because this is what actually cold dark matter means. It means that a species which is actually precisely pressureless. But in our case, we have estimated the phase space distribution, and there is a priori no reason why the pressure component should vanish. So essentially, in order to understand the cosmology of this kind of scenario, we need to go beyond the cold dark matter cosmology and to consider non-cold dark matter. So if we assume then that dark matter is not exactly cold, but slightly could have an equation of state parameter, which is slightly different from 0, well, we can still do this exercise of doing the same thing as we do in cosmology, to expand every quantities around a background quantity, an homogeneous one, plus a small perturbation. And by applying Einstein's equation to these quantities, I can relate the homogeneous part of the phase space distribution to the Hubble expansion rate of the universe, and the fluctuation to the metric perturbation. And by doing a bit of algebra and a couple of simplification, we can show that in the limit where the equation of state parameter is actually not zero, but very small, because we know that lambda CDM is still a very good description of our universe, so we know it cannot be too different from it. In this case, we can actually re-express the matter over density in Fourier space, and it should follow essentially this differential equation. And as you can see, what is important here is that there is essentially one term which depends on the Fourier wave number, which is normalized by this free streaming wave number. And what is important in this context is that the free streaming wave number only depends on the equation of state parameter. And in the case where the equation of state parameter is zero, essentially these terms drops, and the equation becomes independent of the Fourier wave number, meaning that all the mode will essentially grow in the matter-dominated area. And this is typically what occurs in the cold dark matter limit. However, when the equation of state parameter is different from zero, we will actually expect a cutoff in the power spectrum, and this will be given by this scale. And what is important is that this scale only depends on the equation of state parameter and not exactly on the precise shape of the distribution function. And this is a key message here, is that only the equation of state parameter will eventually control the cutoff scale that we should see in the power spectrum. So as I said, this cutoff in the power spectrum can actually be tested by the so-called Lyman alpha forest. So here I'm just giving you the linear power spectrum in terms of the Fourier wave number. And as you can see, the Lyman alpha forest measurement, which correspond to these purple points here, are probing the largest Fourier wave number, which correspond to the smallest physical scale. And this can be used actually to constrain what is called the warm dark matter candidates, which is a dark matter candidate which possess the thermal-like phase space distribution. And if, for example, the mass for this kind of candidate is too small, if I want to saturate essentially the good radio density condition, the temperature for this kind of candidate has to be large. And if the temperature is large, I will tend essentially to smooth out all the overdensity on small physical scales. And this is what you can see in this snapshot as a result from simulation. And I should typically see a cutoff in the power spectrum. So this is constrained by Lyman alpha forest. And Lyman alpha forest tells me that the mass from a warm dark matter candidate must be larger than a few keV essentially. So the precise value will essentially depend on the typical data set that you use and assumption, but essentially it will lie around the keV scale. So as I said before, since only the cutoff, since only the equation of state parameter controls the cutoff scale, I can translate this Lyman alpha bound on the warm dark matter mass into a bound on the equation of state parameter. And if I do this exercise of translating this constraint, I see that Lyman alpha constrained the equation of state parameter for the warm dark matter to be smaller than 10 to the minus 15, which is extremely small. So this actually tells us that the cold dark matter is essentially a very good description of nature, because we know that the equation of state parameter of dark matter must be super small. What is interesting is that these constraints are actually much stronger than what you would expect from CMB, which constrain the equation of state parameter to be smaller than 10 to the minus 10. At this stage, you could wonder, well, then what is the typical equation of state parameter for classical, let's say, dark matter candidates? And for example, if you consider WIMPs, you can express the equation of state parameter in terms of few parameters, but typically this parameter is ordered 10 to the minus 30, which is, of course, extremely small, and essentially there is no way of currently actually testing the non-coldness of this kind of dark matter candidate. All right, so how essentially to translate these bounds into all of our scenarios? Well, since only the equation of state parameter controls the cutoff scale, the idea is just to say, let's find a parameter in a given model that gives me an equation of state parameter which lies precisely on top of the one which is constrained by Lyman alpha. And then I can use this idea to translate the bound from Lyman alpha. So if I do this matching procedure, we can show that we can get an analytical expression for the bound on the dark matter mass in all these given scenario, and it can be expressed in terms of very few parameters. In particular, this quantity T star that I used to define my co-moving momentum, and the second moment of a given distribution of the distribution in a given case. So these are the only two free parameters of this equation. So all I need to know is to compute the second moment of the distribution to determine this quantity T star, and I can rescale the bound. And in particular, if this distribution can be expressed, can be fitted by this simple formula that I showed before, something that goes as a power law and then decreases an exponential. By applying this equation of state matching procedure, I can re-express the bound from Lyman alpha on the dark matter mass in this analytical way here. All right, so this is something that we argued analytically. Well, let's see if this actually works numerically. So in order to check that, we have actually computed the power spectrum numerically using the code class. And in particular, I'm showing here a plot of the power spectrum that you would expect in the case where dark matter is being produced by the inflaton decay, normalized by the power spectrum that you would expect from lambda CDM. And what we have done essentially is to use our equation of state parameter matching procedure to predict the mass. In this case, the dark matter mass that should give rise to a cutoff in the power spectrum that should fall precisely on top of the one we would expect in the warm dark matter case. And we have essentially here three curves because we determine the phase space distribution in three different ways using full numerical computation, analytical expression, and a fit. As you can see, in all these cases, all the curves precisely lie on top of each other, so showing how actually good this equation of state matching procedure actually works. So this is very nice. So we have found a way of translating this bound into a large set of scenarios. And let's see what we actually have in terms of phenological consequences for all these scenarios. So I'm coming back to the case where dark matter is being produced by the decay of the inflaton. And in this case, by using this matching procedure, the bound on the dark matter mass can be expressed in terms of very few parameters, in particular, the inflaton mass and the reaching temperature. And you can see that already for this normalization choice for this parameter, the bound on the dark matter mass can be of the order of the MeV scale, which is already 3 orders of magnitude larger than what you will naively expect if you take the bound on the warm dark matter mass at the KV scale given by Lyman alpha. And in particular, if you take a reaching temperature which is much smaller than the mass of the inflaton, so for example, which could be as small as maybe 10 MeV, slightly above the BBM temperature, you see that in this case, the bound on the dark matter mass can be as high as the EV scale, which is essentially 15th order of magnitude more than what you would expect from the naive bound on Lyman alpha, which is actually very huge, which shows how powerful Lyman alpha can be to probe this kind of out of equilibrium dark matter candidates. Interestingly, if you combine this Lyman alpha bound with the requirement of saturating the rate density as observed by Planck, you see that this actually translates into a constraint on the branching fraction of the inflaton going to dark matter particles to be smaller than 10 to the minus 4. And here you can see that it depends only on 2 parameters, the entropic degrees of freedom of the standard model downward blast, which cannot be much different from 100 essentially. And here you can plug your favorite value from the bound from Lyman alpha. And as you can see, it doesn't depend on any other parameter, which show that Lyman alpha can actually test what's happening in the highest temperature in the universe, and in particular, the coupling between the inflaton and the dark matter particles. And what is actually quite interesting to see is that even though in your specific model, you don't actually have an interaction term between inflaton and dark matter particles in such a way that decay from the inflaton to dark matter particles is essentially forbidden, since you will assume eventually a coupling between dark matter particles and standard model photons, or standard model particles in general, then you would expect the inflaton to decay to dark matter particles, and this will be induced by this quantum correction here. So in this case, this bound on the branching fraction will actually apply as well. All right, so, and well, we can play the same game of looking at the phenological consequences for other scenarios, such as the ultraviolet freezing that I mentioned a couple of times. And as you can see, the bound here in this case is slightly less impressive because we get still something on the order of the Kiwi scale, even though there is essentially a factor of 2 or 3 of difference with the naive bound from Lyman alpha. But this can be translated into a constraint in the plane temperature of heating as function of this lambda high energy scale that I use to normalize the cross section. And here you can use this bound and apply it to your favorite ultraviolet freezing model. All right, so this is just a summary of the main message of my talk. So I hope I convinced you that out of equilibrium dark matter is interesting and that there are a couple of possibilities of producing it in the early universe. And that Lyman alpha is actually a very powerful tool to probe this kind of candidates, and in particular, early universe dynamics. So this is just a summary of the pipeline that we use in the paper and a compilation on how essentially this equation of state matching procedure works well in our case. So there are still many results that are discussed in the paper, so I encourage you to have a look or to send me an email. I will be happy to answer to any question. All right, thanks a lot for your attention.
Thank you very much for the interesting talk. So now the session is for the discussion. Is there any questions or comments? Could you go to the page 18?
Sure.
Yeah, where you used a class to compute the inflaton decay case. So what's class? I haven't heard of it actually.
Class is a cosmic solver that essentially solve a set of coupled Boltzmann equations. So it computes the power spectrum for a given cosmology. So you can, for example, if you have, I think it works also for Axon dark matter particles. So if you have essentially a non-lambda CDM like cosmology, you can use it to compute the power spectrum and also the CMB spectrum and many observables in cosmology. And in particular, if you give it a let's say non-standard dark matter phase space distribution, it can actually compute the power spectrum that you would expect in this case.
Okay, sounds very useful.
It is, yeah.
Okay, so the questions are from Kimiko. Can you ask a question?
Thank you very much for interesting talk. In this case, dark matter is 100% warm dark matter. So if the dark matter is component of both cold dark matter and warm dark matter, is it possible to constrain the ratio of the warm dark matter?
Yes. It should be possible. Yes. The only thing is that in this work, we assume that we only have one kind of dark matter particles, and it's essentially, and they are produced essentially via only one mechanism. But if you have a mixture of cold and warm dark matter, you should expect to see some features in the power spectrum, and this is constrained in some way. But yeah, this is something that we haven't done in this paper. Yes, but this has been explored in the literature, I think.
Thank you very much.
All right, Wen-Yin.
Hi, yeah, I have a question about, maybe I have just missed. So I think you have a slide with the lower bound of the dark matter mass from the inflaton decay. So it's around EEB. So what is the assumption? So if you take the inflaton mass around the heating temperature, I think we can have very,
yes.
I mean, isn't it depend on the ratio of the M5 over the heating temperature?
Yeah, sure. Yes, as you can see on this expression, if you take inflaton mass close to the rating temperature, you would still get a bound on the dark matter mass to be on the order of the MeV scale or small. Only if you have like a large hierarchy between the inflaton mass and rating temperature, you could reach this super high bound. Yes.
You are saying that. So then what is the heating temperature and the mass you take to get the EEV? You are taking the heating temperature MeV and.
So if you keep the inflaton mass to this normalized value of 10 to the 13 GeV, and you take a rating temperature close to the maybe 10 MeV, you see that you get a huge enhancement factor from here, and this boost. Yeah. only if you have a large hierarchy. It means that you will essentially produce dark matter very late, and it will be essentially very hot.
Yeah, it's very boosted. I see. Okay, thank you.
Is there any other questions?
I have a question.
I mean,
so it's interesting. I listened to this talk, but it's more interesting to listen to another talk. So can you go back to the free streaming length momentum formula? So where you said the only information for hot dark matter or warm dark matter is included in the equation of state omega, and in this case the equation of state is for single component dark matter, right? Now you are introducing the averaged equation of state for certain distribution. So I mean but in the case of distribution, you have number density mode number different depending on the momentum, right? I don't know if you are taking equation of state mode by mode, or you are just introducing I mean just the technical aspect of your analysis.
Yeah, so in this case, so the equation of state, so I think I have it on this slide. So yeah, we define it like this. It's essentially ratio of pressure divided by energy density, and it's like an integral of the phase space distribution. So it's the full distribution which is integrated over.
I see.
And they only have different powers for the momentum here, but it's the full integrated distribution.
Okay, I see.
So yeah, so what's important is not the specific features of the distribution, the overall integral.
I see. Overall integral is more. I see. Okay. Thank you.
Okay, any other questions? If not, let's thank our speaker once more. Thank you.
Thanks a lot.
Thank you.
So this is the end of the session. So Hyunmin, do you have any announcement?
Okay, let me introduce you first. The first speaker of the last session today is Misha Shaposhnikov from Lausanne. Why his voice? So he's going to tell us about Higgs inflation and Einstein-Cotton gravity. Please.
Yeah, thank you very much, Hyunmin. Thank you very much, organizers. It's a pleasure to be at this workshop. So I will talk about Higgs inflation in Einstein-Cotton gravity, and the work which I'm going to describe, at least the original part of it, is based on a number of papers which were written together with Andrei Shkerin, who is now postdoc in Minnesota, Sebastian Zell, who is now postdoc at EPFL, and Inar Timirasov, who is now postdoc at Niels Bohr Institute in Copenhagen. So what I'm going to do, first of all, I will remind you what are the different theories of gravity which appeared in the literature during last century or so, and how these different formulations of gravity, what can they do for cosmology, and in particular for the Higgs inflation. So we will see that different formulation of gravity, though for pure gravity they lead exactly to the same dynamics, they induce different physics when the gravity is coupled to matter, and in particular to the Higgs field. And then I will go through Higgs inflation in different theories, discuss the predictions and challenges, and then I come to conclusions. Okay, so short reminder. if we take Minkowski space in arbitrary coordinates, not necessarily Cartesian coordinates, then we can describe Minkowski space by the metric, and connection. Okay, connection is described in parallel transport of a vector and covariant derivatives in a pretty standard way. Then we will find out that the different geometric characteristics of Minkowski space can be hidden in the metric, okay, which is a symmetric tensor. They are given by connection Christoffel symbols, which are symmetric. Then the space is metric in the sense that covariant derivative of the metric is equal to 0. And the characteristic of Minkowski space would be that the covariant derivative commute here. Okay, so this is the Minkowski space, and now we can look at these different four conditions and get away from them to get different generalizations. Okay, so if you talk about Riemann geometry, then the distances are still given by the metric in this way. Then the parallel transport is still given exactly by the same formula. We still have symmetric Christoffel symbols. The space is still metric, so that covariant derivative of the metric is equal to 0. But what has changed now is that the commutator of covariant derivative is not 0. It defines the Riemann tensor, and this is the essential difference between Riemann geometry and Minkowski space. Now, we can give up more conditions than that. Cartan geometry. We still have the same expression for distances. We still have parallel transport, but we have an arbitrary connection in which the gamma is not necessarily symmetric. Okay, so this introduces a new tensor in the game, which is called the torsion tensor, which is the asymmetric combination of Christoffel symbols. Metricity is still there, and as in the Riemann case, we have Riemann tensor. So here we are different in two places from Minkowski space. One can go even further, give away yet another condition, which is condition of metricity. So here you define non-metricity tensor, which is covariant derivative of the metric. This is sub q, which is not equal to 0. And then the space is characterized not only by Riemann tensor, by curvature, not only by torsion, but by the new object. Okay, I will just mention yet another thing, which is also famous, which is Weil theory, in which the non-metricity is not a generic, but which is associated with the vector field, so that the non-metricity tensor is expressed through a new vector field and the metric. Okay, and at that time, at the beginning of 20th century, Weil was trying to use this vector field to describe the electromagnetic field, but it didn't work. Okay, so these are different possibilities which we can have, but since we are interested in physics, not only in geometry, we can ask ourselves what kind of dynamical theory we can construct from all these different descriptions of different manifolds. Okay, so the Einstein-Hilbert metric action. So metric, it will be the second theory in which we don't have torsion, is the following. Everybody knows it. It's the measure times the scalar curvature. And since in this metric case, our dynamical variable is the metric, we can take this action find out variation of this action with respect to metric, and then we will derive Einstein equations of motion. Yeah, now we can ask ourselves, okay, suppose that we have different types of fundamental dynamical variables. And now we are coming to Palatini action, though in fact it was also invented by Einstein. Okay, so we can say what we have at hand is the metric which describes distances. We have at hand symmetric connection, and we still have the same expression for the curvature in terms of connection. We can still write the same action, but now treat G mu and gamma as independent variables. Okay, and then if you go through this elementary procedure, you find out that variation of this action with respect to the connection would give us metricity, and so metricity is not imposed, but it's a dynamical consequence of the action. And then once you find the variation of this action with respect to the metric, at the end of the day, you get Einstein equations which are exactly the same as in the previous case. So this happened to be exactly the same formulation at the end of the day. One can say, okay, so let's go even further and let's consider the case when we have Einstein Cartan, so Cartan geometry. There we have distances, we have connection, which is not necessarily symmetric. And again, we can write an action for the pure gravity, which now allows more structures. Okay, so this we still have the curvature tensor, but we have also the torsion tensor, and in addition to the Einstein-Hilbert term, we can have yet another term here. In the metric gravity, this guy would be equal to 0 because of symmetries of R mu, but now it's not equal to 0 because the connection is not symmetric. So the theory at first sight is characterized by two parameters, one in the Planck scale and another is coefficient in front of this last term, which is called the Barberi immersive parameter. And again, you take this action, find out variations, etc., and you find out at the end of the day that you get the theory, which is exactly the same as the Einstein gravity, so that even this theory is the same as the initial one, so that Einstein-Hilbert formulation happened to be extremely stable from that. Whatever you take, you get one and the same thing. Okay, so in fact, the Einstein-Cartan formulation happens to be, though it leads to the same, exactly the same equations of motion, kind of conceptually, it's a very interesting formulation, which is very close to what we have at hand in particle physics. In particle physics, we have different gauge symmetries. Standard model is based on the gauge symmetry SU3 cross SU2 cross U1. And the gravitational field is considered on a somewhat different footing. We're talking here about geometry, etc. Of course, the question arises, perhaps the existence of gravitational field can be also related to different gauge symmetries, and the answer happens to be yes. You can promote the global Poincare invariance to the gauge symmetry, and the different approaches formulated in 50s, 60s by Utiyama, Kibo, and Siyama indeed demonstrated that the gravity itself can come from the gauge principle. Okay, so here the basic gauge field happened to be tetrad, which is the gauge field of translation, and there is a field associated with the localization of the Lorentz group, which is spin connection. Okay, and by using this type of formalism, we can also write the lowest order action for these gauge fields. It is written here, and it's expressed through the Shaposhnikov form, through the field strength. And again, if you go through the normal formalism variation with respect to dynamical parameters, equations of motion, you will find out that again, this formulation is equivalent to the very first metric Einstein gravity. Okay, in fact, this equivalence of different formulation is lost when matter fields are added. And this happens because of the following reason. Okay, if you talk about scalar fields, and you do have a scalar field in the standard model, for instance, then we can have a coupling of different geometrical quantities, okay, in different formulations of gravity to the scalar field, like here, okay? So here, this is a non-minimal coupling for the scalar field to the scalar curvature, and this is the similar term written in the gauge language. Also, when we consider interaction of different matter fields, such as the fermion fields, we also get the terms which are associated with the connection. And the presence of these terms and these terms lead to different type of physical contexts of different gravitational theories based on different dynamical variables. Okay, so here in this talk, I will be interested in inflation. Inflation is associated with the scalar fields, so I will discuss in more detail the scalar sector of the standard model plus different formulations of gravity. Okay, so let's take Higgs field of the standard model or generic scalar field, it doesn't matter, this is just the name. In the flat Minkowski space-time, we would write this type of action. For it, we have kinetic term, we have potential, and this is a generic potential. Couplings. Oops. Is it okay, Honmin?
Yeah, yes, okay, yes.
Okay. No, I had something here. Okay, so and then we have different terms, how the scalar field interacts with different geometrical objects. Okay, and I'm choosing now the case of Einstein-Cartan gravity, where we have not necessarily symmetric Christoffel symbols, and metric and Christoffel symbols are independent variables. Okay, so we have a usual gravity term, Planck mass times r. Then we have non-minimal coupling of scalar to r. Then there is the term which carries the name false term, where we have this object times the Planck scale. Okay, there is some parameter here. Then again, we have non-minimal coupling. And also there is the term which is associated with the Young invariant, which is written here. And this is again the square of the scalar field times certain combination of the torsion. Okay, so why I selected this type of action? This type of action is selected from requirement that it's first polynomial, it doesn't contain any strange powers of the scalar field, and also the action is scale invariant in the limit when the scalar field goes to infinity. Okay, so this question happened to be related very closely to inflation and to the shift symmetry, which is which eventually leads to inflation. Okay, so
what does this T length tensor?
Sorry,
what does this T in the invariant? This T.
This
the last one T nu rho sigma. This T tensor at the last term.
Yeah, this last term.
What does this T describes?
Okay, so here is in this last term, we have T is the tensor associated with torsion.
Just torsion.
Yeah, so this is just torsion. Okay.
Oh, I see.
Yeah, okay. This is torsion, and this guy is here. This one, this one, this one, and this one are all dimensionless parameters which just characterize this theory, and these parameters are a priori unknown. Okay, and this guy is just the torsion, Okay, and this is the unique action which can be written from the following requirements, that you get equations of motion which are of the second order, and this is the action which is invariant when scale invariant when the scalar field is very large. Okay. Okay, so what's if you take this generic Lagrangian, then going through the standard procedure of finding equation of motion, resolving constraints, etc., you find out that torsion, though it is present in the Lagrangian, is in fact non-dynamical. Non-dynamical means that it is expressed through other degrees of freedom. So this theory, it has the same number of degrees of freedom as you would have in the metric gravity, meaning that you have a graviton and a scalar. Okay, this Lagrangian has an interesting physics, that if you consider the scalar fields which are very, very large, okay, then as I said, this Lagrangian is scale invariant, and therefore all couplings associated with the gravity scale in the same way as the scalar field. So we get a dynamical Planck scale, which is psi h squared. Okay, and this is a great thing for inflation, because this leads to the flat potential for the Higgs field when it is large. Okay, so how to analyze the theory? Here, the best thing is to use the machinery which was developed for the study of inflation for single field models. Okay, and here the frame of choice in the Einstein frame, in which the Planck scale is non-dynamical and just equal to some number. Okay, and we can go to this frame by making a conformal transformation with the method. And if this is done, this is the action which you are going to get. Okay, so you see here that you have this term, which is nothing but the Einstein-Hilbert term, and then we have a specific kinetic term for the scalar field, for the Higgs field, and specific potential. Okay, so this potential U, which we used to have previously, is now divided by this function omega, which is specified here. And then there are different complicated terms which are associated with the kinetic term for the Higgs, which contain all these non-minimum couplings. Okay, and so if you look at the potential itself, then it generically has this structure. Okay, there is some minimum at small values of the scalar field, which is associated with the minimum of this potential. Then there is a plateau, and this is a great thing for inflation. And in fact, this theory here, it unifies many theories which were considered previously for inflation. So, for instance, metric Higgs inflation correspond to some particular choice of different non-minimum couplings. If you start from the Palatini theory, then another choice of parameters leads to the Palatini action. And if you consider generic case, then you get a generic Einstein-Cartan theory and generic Einstein-Cartan Higgs inflation. Okay, so how the inflation goes here, generically, there are several stages. At the very first stage, if you consider this scalar field which is sufficiently large, then it will slowly roll down towards phi equal to 0, inflating the universe. If the initial condition is at small field phi, then nothing happens and this regions collapse. Then the next stage of inflation is reheating. When the Higgs field, scalar field arrives to some value, it starts to oscillate here and produce a hot Big Bang. Okay, and after that, the radiation dominated stage of the expansion starts. And this leads to everything what we have in the Big Bang theory, baryogenesis, dark matter production, nuclear synthesis, etc., etc. Okay, so let me show you why we get different predictions for different choice of these non-minimum couplings, and so what is happening there, why the difference appears. Okay, so if you take metric Higgs inflation, okay, we have this action, okay, simplest one, and once we go into the Einstein frame, okay, we get a kinetic term for the Higgs field, which has this specific form. It contains the this conformal factor plus extra thing. And if you now analyze this theory, you find out that you get a correct amplitude of the scalar fluctuations if non-minimum if non-minimal parameter at psi is related to the scalar coupling constant with some coefficient which is of the order of 10 to the 5. Okay. Now, if you do exactly the same, but now with Palatini Higgs inflation, okay, so the starting point is exactly the same, but since you get different dynamical variables, then the kinetic term for the Higgs field in the Einstein frame actually has a different form, which leads to conclusion that the psi parameter has a different, should be different. The relation between psi and scalar coupling is different to get the correct polynormalization. And so this theory, because in the Einstein frame they have different form, they lead to different predictions. Okay, so this is a busy slide, but this is a slide which summarizes the different physical consequences which appear in these two different formulations. One is the metric formulation, and another is the Palatini one. Okay, so in the Einstein frame, these two theories are given by this action, and but this function k, which I already mentioned, they have different form in the metric and Palatini case. So this leads to different potentials for canonically normalized field. For the Higgs inflation, this is here. For Palatini inflation, this is here. This leads to somewhat different predictions for the number of n-foldings. It gives somewhat different predictions for the scalar index, and that leads to very different predictions for the tensor to scalar ratio. Tensor to scalar ratio for the metric Higgs inflation is on the order of 10 to the minus 3, whereas for the Palatini case is much, much larger. And actually, theoretically, the study of Palatini inflation happens to be more clean than the study of the metric Higgs inflation. And this is all associated with the fact that in the Palatini case, the UV cutoff, so the energy at which perturbation theory breaks down happens to be parametrically much larger than for the case of the metric Higgs inflation. Okay, so here I just put different predictions for that. So this is the case of a Higgs inflation in metric case and in Palatini case. So this is the picture which shows the prediction of different theories. Predictions of metric Higgs inflation are very close to predictions of the very first inflationary model by Starobinsky. And here is the close-up of this point. Okay, so this is the scalar index, this is tensor to scalar ratio. Metric Higgs inflation gives about 10 to the minus 3, whereas Palatini Higgs inflation gives about 10 to the minus 10. Okay, so these were just two particular cases of the choice of different parameters, but in fact now we have a theory, and we don't know a priori which one to choose. Once we have Einstein Partan formulation, it's plugged by different non-minimal couplings. And what one can do, one can look at generic Einstein Partan Higgs inflation, which is which would correspond to generic choice of different non-minimal couplings. Okay, and here is one example. So what we call the Nian-Yan Higgs inflation, we put some of the non-minimal coupling equal to 0 and another going to infinity. And then, so what these two pictures show, they show what is the spectral tilt here, and here is tensor to scalar ratio. Okay, and so what you do, you look at this curve, okay, and the NS is given by the color code along here. Okay, and then you see that one type of inflation, like polyphony, is continuously joining the metric Higgs inflation. Okay, and then this is the same for R, and you see that there are domains where the tensor to scale ratio are pretty large, of the order of 10 to the minus 2. One can do even more profound analysis, choosing these couplings in some arbitrary way and see what kind of predictions for the scalar tilt and for the tensor to scalar ratio you can get. And this pictures shows how often this and this values for the scalar tilt and for R appear for different choice of parameters. Okay, so let me summarize the results of that study. So first, we see that independently on the choice of different non-minimal couplings, the inflation is actually a generic phenomenon, okay? And it appears, it happens almost for any choice of these couplings. It happens that the metric Higgs inflation and the polyphonic Higgs inflation are kind of the attractors in this big plane. So large parts of parameter space reproduce the predictions of either metric or polyphonic Higgs inflation. In almost all the cases, you find out that the scalar tilt is almost independent on the choice of different couplings and very close to what we have for polyphony inflation or Higgs inflation, 0.96. At the same time, the tensor to scalar ratio is not stable and depends on this parameter. And basically, you can get any value between 1 and 10 to the minus 10. Okay, so this is an interesting thing. When this story, the Higgs inflation, started, I myself thought that, okay, we have a very solid prediction. We know what NS is and know what R is. And now we see that this is not true. So this is true, it's just partially true. This is true for the scalar tilt, but this is not true for tensor to scalar ratio. A priori, we don't know what kind of variables to choose, what kind of formulation of gravity to choose, and the answer to that do depend and depend strongly on the formulation of the gravity field. Okay, so let me now go through challenges which appear in different computations and different conceptual challenges. So the first one is common for all types of inflation. Okay, since we add gravity to the theory, the total theory is not renormalizable, and question appears: how do we find quantum corrections to that, whether this classical picture, which I discussed up to now, is modified when quantum effects are included. Yet another challenge is that if you talk about Higgs field and the standard model, then the standard model parameters they are all measured at small energies, 100 GeV, whereas inflation takes place at high energies. And so we have to extrapolate a lot. If we extrapolate the standard model coupling, it may happen that the scale of self-coupling gets negative at large value. And if this happens, then we have Higgs inflation. Okay. The first challenge can be reformulated in the following way. Okay, we can add to. So the question is, what is the validity, perturbative validity of the scale of gravity theory with non-minimal coupling? Okay. So we can take this Lagrangian, we can take different formulations of gravity theory and ask ourselves at which energies we can trust our computations, at which scale we get the large corrections. Okay, so the answer to this question already happened to depend on the formulation of gravity which we use. If we take the metric theory, then for zero scale of the ground, this cutoff happens to be of the order of m Planck of xi, and this is small compared with the cutoff energy scale of inflation, which raises doubts that we can use this Lagrangian in the inflational domain. Now, if you take Palatini Higgs inflation, then this doesn't happen. It happens that the cutoff for zero of the ground is parametrically somewhat smaller than the scale at which inflation happens. So here, this doesn't make any problem. Okay, so should we say that, okay, this is the theory to take, Palatini, we should disregard Higgs inflation in the metric theory? And the way to proceed, there could be different ways to proceed. So one way would be to say, okay, let's add new fields and construct a theory in such a way that for zero Higgs and other field at the ground, the inflation occurs in the weak coupling regime. This idea belongs to John Judici and Fumi. And there were many generalizations in this direction. Or there could be yet another way to look at that. One can try to go beyond the naive power accounting and construct a refined effective field theory of Higgs inflation. Okay, so if you take the second road, then the following happens. Since inflation occurs at large field domain, we can reanalyze the question of the strong coupling into the ground of the non-zero Higgs field. And if we do so, we can find that the cutoff, this limit at which the energies are, the energies are above this number, the theory enters into strong coupling regime. This is this here, and this is the phi field. It depends on the cutoff, and it happens so that the strong coupling domain is actually above the inflationary scale. Okay, and this means that in fact the computations which were done even for the metric Higgs inflation are all self-consistent. Yet another problem, which I also mentioned at the very beginning, is possible vacuum metastability. If you look at the behavior of the scalar self-coupling as the function of energy, then depending on the standard model parameters measured at low energy, such as the mass of the Higgs boson and the mass of the top quark, we can find that the scalar self-coupling crosses zero at energies which can be as small as 10 to the 10 GeV, or it can never do so. Okay, And so what would happen if we have this crossing at smaller energies, and Higgs inflation survive that? Okay, whether this crossing happens or not, we don't know. The crucial issue here is the measurement of the top quark mass. And if the top quark mass is smaller than some value, this crossing never happens. If it's smaller than this number, then this crossing happens. And whether this happens or not is kind of 1 sigma uncertainty. So you take the measured value of the top quark mass, you vary it within the experimental uncertainties, and you see that, okay, so this is the central value, and this is the place where we go from stable to metastable vacuum. So this distance is about one from 2 sigma. Okay, so we don't know that. The question. So I have what, 5 minutes?
Yeah, you have 7 minutes.
7 minutes. Okay. Okay, then I'm fine. To see what happens at high energies, depending on this behavior of the scalar self-coupling. So we have 3 types of possible naive pictures. So if the scalar coupling never crosses 0, we have potential like this. If the scalar coupling exactly touches 0, we have this type of potential. Or if the scalar coupling crosses 0 at some value, then we go up and then we go down. And if you look at, say, this picture or that picture, we can ask ourselves, can we have Higgs inflation at all? Because we are supposed to be here at large field phi, and then how comes that we appear at this stage? Okay, but in order to address this question, there is a challenging problem to solve. Okay, so RG equations, they do not take into account all this gravity effect if we talk about RG equations in the standard model. And so how do we account for different gravity effects? Okay. The minimal approach to minimal setup, which one can use, is the following. We take our non-normalizable theory, which contains the standard model and which contains the gravity, and we add all the counter terms which make the theory finite. Okay, if the theory is normalizable, then the number of counter terms which you have to add is finite, and this makes the theory predictable. Now, since we have gravity, we have all sorts of non-normalizable interactions. We can also do so. We can make the theory finite. However, we have to add the infinite number of counter terms. Okay, and then the theory is not predictable at all energy scales. It is still predictable at small energies because this is an effective field theory, but at large energies, this theory is not predicted. Okay, but still, by doing so, we can parameterize our ignorance about high energy parameters by few numbers. Okay, and the essential numbers can be found, and this ignorance can be parameterized by a number of parameters. Okay, so I'm not going to go through this in detail through this program and just outline the results. So the Higgs potential is well defined for the scalar fields which are smaller than m Planck over psi. Okay, so I'm talking here about the metric Higgs inflation. For Pontini, this is not needed at all. The inflationary Higgs potential is also well defined for the scalar fields which are larger than that. However, this part can be expressed through low energy standard molecule parameters, but this part is expressed through low energy parameters and some unknown matching coefficients, which describe what we call the jumps of the couplings at the field value, which is of the order of m Planck over psi. Okay. And then independently on this matching coefficients, the predictions of the metric Higgs inflation remain in place, though details about reheating, and stuff like that are not determined. And moreover, there are some matching coefficients in which the Higgs inflation can be realized even for metastable lab. But here I would like to stress that, okay, so these are results specifically for metric Higgs inflation. Once you go to the generic Einstein-Cartan case, then the uncertainties, in particular in this number, are much larger. Okay, and I think that I come to conclusions now. I think that Einstein-Cartan gravity is an interesting theory with the following properties. So first of all, it generalizes the metric formulation of the Higgs inflation. Introduces more parameters, but it's richer. This theory, it has the same number of degrees of freedom as the metric gravity, graviton plus the scalar field. The Higgs inflation and the hot Big Bang, where the reheating temperature, which is pretty large, at least greater than 10 to the 30 GeV, is the natural consequences of this theory valid for most part of parameter space. There is a universal prediction for the scalar field, but there is no universal prediction for the tensor to scalar ratio. Okay, and so it can be large as present experimental limit. And so if this theory is right, we may hope to see observable tensor to scalar ratio. And there are other topics which are not related to inflation, which are also, I find very interesting, is that I didn't talk here about fermions, and it happens that the Einstein-Cartan formulation automatically leads to a new interaction between different fermions. This is four-fermion interaction, and phenomenologically, this interaction may be interesting as it gives another way to cosmologically produce very weakly interacting particles. And these very weakly interacting particles could be fermionic dark matter particles. And also, there are non-perturbative effects in this theory, which may lead to an explanation why the Fermi scale is much smaller than the Planck scale, and this is related to existence of some non-perturbative semi-classical effects associated with a new type of singular instant codes. But this, of course, I have no time to discuss. Thank you very much for your attention.
Thank you very much for your interesting talk and the extension of Higgs inflation. So now it's open for questions, some comments.
I have a question, if that's okay.
Yes, Pierre, yeah.
Yeah, so for the Einstein-Cartan theory or for non-metric extensions, are there low energy corrections to gravity, either in terms of propagation of gravity waves or solar system position measurement, etc.?
No, there is absolutely nothing, because this is a modification of this theory in UV and not in the infrared. In the infrared, you have exactly the same things around in the metric. Okay, so we are depending on these parameters, psi, etc. The whole theory requires several scales. So one scale is, of course, the Planck scale associated with gravitational interactions. And then there are lower scales like m Planck divided by square root of psi or m Planck divided by psi. Okay. Above the scales, there are deviations from metric gravity. But below the scale, there is absolutely nothing. So there is just massless graviton and the Higgs field.
Thanks. Maybe one more question, Yunmin, is it okay?
Yeah.
In the metric theories, do you have a clear prediction for the top quark mass, for example, or the top and the Higgs? So you need it to be stable, right, for the metric theories?
Well, in the Higgs inflation, if you take the metric Higgs inflation, okay. In the metric Higgs inflation, as I said, there are uncertainties because there is a at this cutoff scale, like m Planck divided by psi, some uncertainty entered into the game, which tells that you cannot trust low energy RG behavior for your beta functions. Okay. Now, if you say that these uncertainties are small,
well, you need it to be valid at 10 to the 11 GeV, right? It's not that.
Well, let me show you one picture so that this will be more clear what I have in mind. Okay, so let's take the case of metric Higgs inflation. Okay. So what this picture, and let's look at these two pictures. I will explain you in a second what these two pictures mean. This is the scalar field, and this is the potential. Okay. So imagine that the top mass is large, so that the vacuum is metastable, and the scalar coupling crosses 0 at 10 to the 10 GeV. Okay, then the potential looks like this, and then you would say that no Higgs inflation is possible because the system cannot go in this way. However, at the scale which is much larger than 10 to the 10 GeV, which is m Planck over psi, new physics happens, and this new physics is actually associated with the jumps of different coupling constants, in particular the scalar coupling constant. And we don't know what is the amplitude of these jumps, and we don't know what is the sign of the jump. So if this jump is such that the potential still remains to be negative, then Higgs inflation doesn't occur, and then that leads to a upper bound on the Higgs on the top mass, which is about 171.5 GeV or so. Now, if at this point there is another type of jump of the coupling constant, which brings the potential to this form. So instead of going down, the potential goes up. But then in this case, Higgs inflation is still possible, because what happens here is that Higgs field rolls down towards the minimum. The universe is reheated, the symmetry is restored, and the Higgs field comes to phi equal to 0. Okay, so here I would say that we don't know if these jumps of coupling constant, because of reasons which you don't understand, are very small, then yes, there is an upper bound on the top mass. If these jumps are making the potential in this form, then even sufficiently large top masses are harmless for inflation. And this is an open question.
I think that we don't have much time, but Ko, maybe you may ask a short question.
Could you briefly, could you briefly describe about UV completion, the slide you skipped?
Well, the UV completion, I kind of completely ignorant. I mean, I cannot say what the UV completion of this theory could be. Okay, this would be.
You have on slide, so I was wondering what it has.
Well, UV completion, okay, maybe it's asymptotic safety. I don't know. UV completion, I mean, I cannot give any reasonable answer to your very important question.
Okay, thank you very much.
Thank you for your nice talk. So let's move on to the next speaker, Jan Mambrini. Maybe, okay.
So I stop share, right?
Yeah, you should stop sharing. Yeah. Then, Jan, okay. You can share your screen. Okay. Okay, you can make it to the full screen. Okay. Okay, thank you. So next speaker is Jan Mambrini from University Paris-Saclay. He will talk about dark matter production in the very early universe. So I don't hear you, Jan. Your audio.
Yeah, now you hear me.
Okay, now I can hear you.
Yeah. So thank you, Yumin, for the invitation to this nice workshop and all the organizing committee. I would say it's always a pleasure to come to Korea, but this case is quite remote. So yeah, I will discuss. I think I planned too much slides for 30 minutes, so maybe I will not have time to go to the end. So I will stop when I should stop. Just tell me to stop. So I will try to discuss about the dark matter, matter production in the early universe or very early universe. So my talk will be valid for dark matter, but in fact, it will be just to try to explain mechanism of production of matter during a phase that we call reheating and preheating, which is a phase just after the end of inflation. So what we call preheating is mainly the first oscillations. There is no really bounds, exact bounds between preheating and reheating. But let's say 10 to 21st oscillation of inflaton is preheating, and after it begins to be reheating. Okay, more or less when the frequency of the oscillation is larger than the expansion rate. So a little, the work has been made by Keith Olive and all of us, and a little word for the PhD students. Okay, Simon Clay, which is my students, and Paris-Saclay and Saunas Werner, which is a student of Keith Olive. So Saunas will be in Florida University for a postdoc, and Simon just beginning his PhD thesis. A little publicity too from the book which has been released. My book, which has been released in November, don't hesitate. It's a guide to, where I try to combine cosmology and particle physics in one book. It's I think is mainly due if you teach, for instance, particle physics. I think can be very useful for students. We can discuss about it also another time. So my talk will be divided into 4 main parts, which is the generalities of what we know people I think, have in mind about reheating. And then I will go into details into two specific process, which is non-instantaneous reheating, which is a little bit less known, and the preheating phase, which is, I would say, very well known for some people and completely unknown for other people. And I will try to apply, if I have time, to gravitational production, which means production of particle from exchanging a graviton. I mean, so in the case, the graviton would extract from the inflaton condensate the energy to produce particles. So a brief story of the energy in the early universe. So a lot of different phases, as you see. So you have a phase of inflation, of course, that everyone knows. And this phase of end of inflation, where you pass from potential, which is almost constant, at least slow rolling, to a potential, which is, I mean, a field which is oscillating, is called the reheating phase. And in this reheating phase, you can also divide it into a phase where the radiation is not thermal, and the phase where the radiation is thermal, but still not dominating the universe. And what is officially called as reheating temperature is the time in the universe where the inflaton begin to, or I would say the opposite, where the radiation begin to dominate on the inflaton. So sometimes in the mind of people believe reheating temperature is the maximum temperature of the universe. Is not the case. The reheating temperature is just the temperature of the thermal bath when the inflaton more or less has been completely decayed through scattering or through annihilation or through decay. So and you have a phase, a certain temperature of universe, if you want, where you a time in the universe, if you want, where you can define the temperature because the thermal equilibrium appear. Okay, so before you don't have thermal equilibrium. So a phase of inflation, a phase of matter domination. What I call matter domination, in fact, is not true. Is more inflaton domination. It's matter only if the inflaton has a quadratic potential, as you will see, which is not always the case, and a phase of radiation domination. So let's begin by this phase here, okay, of what we call the end of reheating, which is most known, I think, by all of you. I would call it the thermal reheating in a sense. So after several oscillations, for instance, what we call the reheating phase. So to understand and to see how the transfer of energy from the inflaton, because the reheating is just a transfer of energy from the inflaton, from the energy stored in the condensate of the inflaton to radiation or to whatever it can decay. So the game is quite easy. You just have to solve, of course, the equation of conservation of energy, of Riemann equation, whatever you want to call them, and to transfer to translate it as an equation for the field of its inflaton. The field will be considered as homogeneous in the first part of my talk. So this is zero, no grad of the inflaton, because it's a condensate, but this condensate will be transformed, as you will see, as a classic, as a quantum field and a field of as a particle, from condensate to a particle. So from what we call back reaction effect, but I will come back to that at the end of the talk. Up to now, my field will be considered as homogeneous. Okay, so just depending on time, it's a condensate. And so you solve the equation. It's very easy to solve the equation for phi. Okay, for rho phi, just by this equation, you can put it back, and conservation of energy give you this relation. So you see you have a dependence on the shape of the potential. So I take, okay, potential which has this kind of form with phi power k, but you can take any kind of potential because we are doing the phase of oscillation. So we are not really restricted by any kind of data, and any kind of potential you have, you can always suppose you can develop it as in a polynomial form, whatever is the shape of your potential. So it's always possible to develop your potential in a polynomial form. So k does not have to be equal to 2, for instance, can be quartic, can be even power 6, whatever it is, depending on your potential. Alpha attractor model, for instance, have different power of phi, which is 5 to the 4, or even 5 to the 6. So it's very easy. So you see that inflaton condensate evolve, in fact, as function of scale factor. I is the scale factor, okay, as the power of the scale factor. And you recover for that for a quadratic potential. So k equal 2, you recover the power 12 divided by 4, which is 3, a minus 3. A minus 3 is a typical evolution for a matter field. That's what I call matter domination. This is, I will say, 95% of the paper consider an inflaton and a quadratic potential, which is quite normal because it's a minimal potential you can imagine during the oscillation period. And you notice that if I take k equal 4, for instance, so if I take a quartic potential, give you 24 on 6, which is 4, a minus 4, it's a radiation field. So, and of course, if I change k, go to the maximum to a minus 6. A minus 6 is a case of k going to infinity. So rho phi can evolve from, let's say, a minus 3 to a minus 6, depending on the nature of your potential V of phi. That's quite important because in the literature, and I think in the popular idea, it is that rho phi behave like a matter field, and I can define a density n phi, which is rho phi divided by m phi. The energy is m phi, etc., etc. So all what you see, which is true only in quadratic potential, makes sometimes you believe or treat the inflaton field as an inflaton particle, as an inflaton matter particle, because its evolution as function of scale factor is the evolution of a matter field, and because a lot of calculation has been made as a quantum field. But phi is just a classical field, okay, which is homogeneous. So it's important to keep in head that it's a background field which is homogeneous and which should be treated as a classical field, not as a quantum field. You will see there is some subtleties between these two differences when I will go to the expression concerning the back reaction effect. So if you solve the equation, as you see, so it's easy to understand. So for instance, if I take a mix of quadratic plus quartic potential, you understand quite well that for large value of A, okay, when A dominates, when A increase, it will be dominated by the matter nature of the inflaton. So with phi to the square, which is A minus 3, okay, so this rho phi will behave like a matter. But you see that at the beginning, of course, when I is much smaller, this term will dominate, okay, and you have an evolution, which is phi to the 4, which means A minus 4, as I told you, which is radiation field. So just to show you that just having quartic plus quadratic potential term in the potential show you that phi is not a classical field, okay? You cannot consider it as a radiation field or as a matter field. It really depends where you are in the process of reading or operating. So we really had to treat it as a special field in this sense, okay? And in this case, of course, you understand quite well that the phase transition, I will say, between a radiation field and a matter field will happen when this term dominates on this one, okay? So it's just to show you that you have to be careful with that. So now if you want to make reading operating, of course, you have to add a coupling to matter, okay, or to any kind of other field, I will say. So I will first couple it with a classical Yukawa term, okay, so with a fermion-like particle if you want. I will not yet couple it with a scalar particle, just coupling it with a fermion. So in this case, the equation changed a little bit. From this equation, you have this equation, okay? So you have to add, a dissipation term, okay, which corresponds to a decay of the inflaton. It could be also a scattering, as we will see, but now it's a decay. And the naive way of looking at the preheating or the reheating is to suppose that the decay happens more or less at the time corresponding to the width, to the inverse of the width of the inflaton. And at this time, all the inflaton decay and the reheating temperature is given by the lifetime of the inflaton, which is a little bit naive way, as you understand quite well, because in fact, you really have to solve all these equations. So this naive way is called instantaneous reheating, when you suppose you are dominated by the inflaton, and at a time corresponding to the lifetime of the inflaton, all the inflaton energy is dissipated and is transferred to the radiation. But of course, it's not what's happening. The reheating is a process which is continuous, so you have to solve this equation continuously from the end of inflation to the more or less end of reheating. And so solving this equation gives you an evolution which is, of course, much more different, and give you a temperature which depends, as you can see, of the potential, of course, of your inflaton. So it's important to notice that, of course, the temperature is not A-1 as as usually people think, mainly because, as you understand quite well, you don't have entropy conservation in the thermal bath, because thermal bath is alimentated, if you want, by the energy of the inflaton. So the system is not closed. The thermal bath is not a closed system. It's an open system and is open by the inflaton. This inflaton plays the role of hot source, which hot drop of liquid into a cold source, and so will heat the cold source little by decaying. So the temperature evolves differently. And you can also understand why it depends on K, because the inflaton itself, if it behaves like a radiation, it will be redshifted with time. So the density of inflaton will lose, of course, energy from the fact you have expansion of universe, but will also lose energy by the fact you redshift itself is energy. This, of course, does not happen if it is a quadratic potential, but if you have a quartic potential, I have a dilution due to the expansion and to the redshift effect. So that's why the temperature of your thermal bath depends a lot on the potential of your phi, because the potential of your phi give me the nature, let's say, the equation of states of phi. So if I add now another coupling to the inflaton, which is a coupling this time to scalar field, suppose it's a Higgs field, for instance, you can suppose right on the neutrino and Higgs field here, if you want to give name to this F and chi, but okay, it's not important in my case. I don't consider any kind of typical particle. I will first begin by having a coupling which is much smaller than m phi square, sigma phi square smaller than m phi square, which means the effective mass, because you see that this will be an effective mass. The effective mass of the Higgs, or the effective mass of the scalars that I produce, I first consider it much smaller than the mass of the inflaton. So that's quite important, because you see that for certain kind of coupling, you can have an effective mass here, which will be much larger than the mass in the inflaton. What it means that in the case of the quadratic coupling, m phi being the energy of the inflaton stored, because quadratic coupling m phi, inflaton is like a dust. In this case, you can block the production effects. Okay, so it's quite strange, but if I increase too much my coupling of my inflaton to my radiation field, which can be the Higgs, I have a possibility to block it, in fact, because the effective mass that I will produce from the oscillation of the inflaton, which has to be treated, I told you, as a classical field. Don't forget, this is just a parameter, okay, we depend on time. This is not a quantum field. So I produce an effective mass which can be above the energy which is stored in inflaton. So I just have a kinetic blocking. So I will consider a small mass here. So this is what I represented. So you can produce the fermion from the decay and the scalar from the scattering. And so just to show you how it evolves with time, so I just take a Yukawa, which is the same now that the coupling to the Higgs, if you want, to the scalar, which is 10⁻⁷, just to give you an example. So I have the evolution of rho phi. In this case, I take a quadratic potential to render the things easier. So my rho phi evolve as the dust, okay, but you see that I don't have the same evolution for my radiation produced by the decay and for my radiation produced by the scattering. One will evolve like a radiation field, okay, and the one will evolve like a dust field. And here, this little region, I will come back after. This is where this effect of the effective mass is quite important. And you see you have a reduction already. You can see a little reduction here from the fact you have a reduction from the fact that the phase space begin to be, closed, because the effective mass here for large value of phi, okay, which is at the beginning of the time, phi is quite large. In this case, this effective mass can reduce quite largely the production of the scalar. Okay, so you clearly see quite well here in the phase. So you are dominated first by the scalar, and then you are dominated by the inflaton, by the fermion, the bath, and here the rating temperature, it is when both reach, in fact, the value of rho phi, and this is the rating temperature when the inflaton completely disappeared from the bath. So I just want now to go a little bit earlier in the universe and seeing what's happening in the first oscillation, because here the physics is completely different in this case, because you have what we call parametric resonances. So I want to insist a little bit about it, because this is a little bit, as I say, this field is very well known from part of a community, but completely, I think, not known by another part. So that's why I want to be quite pedagogical on this region. So this is this region I was discussing here, which is just at the end of the inflation. So in this case, the equation you have to solve is, of course, the same. So this is the equation you have to solve for the production, okay, for the particle scalar which is produced. So it's quite similar to the equation of the inflaton, of course, but this time is a quantum field which is not homogeneous. So I have to take care of a momentum of modes, different modes, if you want. And this is a production term. Okay, so you see that if I developed my field under its different mode P, so I have to solve this kind of equation for each mode. And this is what we call a Matthew equation. In the case of quadratic potential, it has a different name because it's the case of quadratic potential. I will mainly stay in quadratic potential up to now, just for the explanation. Matthew equation, in fact, is a kind of harmonic oscillation, but whose parameter is itself oscillating, is itself periodic. So it's an harmonic equation with a parameter which is periodic. So it produces resonances at a frequency which is half the frequency which is forced. So this happens in a lot of systems, and so it's not proper to inflation, of course. So I'll show you here a little video to show you what's happening. So you will have here the forced frequency, which is this one. Okay, so you have a system which has a frequency, proper frequency, and the frequency you force corresponds to the one you put here in the hand. So when you have a frequency in the head, it will correspond to half of the frequency of the harmonic of the oscillator. You see that you have a resonance, a production which is parametric resonance. Boom. Okay, you have the explosion of the production. So you have to transfer it to the inflaton. You have to suppose that the inflaton is the one who forces the oscillation, and this is the radiation field. So the same here. You have a kind of a spring here. And you see that if I have a frequency which is classical, you don't have any kind of oscillation. But if here I fix my frequency half the one of the spring, you will see appearing. So this is a particle produced. Imagine this is a particle produced, and this is a background field here, which is inflaton. So when you see you begin to have resonances, exactly when this particle that you produce have an energy, if you want, which is half the frequency which is here, which is 2m phi. Okay. So it's normal because you have 1m phi. So energy you produce has the energy of m phi because you have scattering. So this is exactly what's happening in inflaton. So inflaton is a field which oscillates, okay, and his oscillation, which is forced production of particle by resonant effect. So if I put a little plot here where you have the effective mass, which is related with the inflaton, and the mode, which is produced, which is of course redshifted by the expansion of universe. If I evolve in time, I go from this value here, the time I will have the inflaton which decrease, and my mode will decrease by the redshift, and my inflaton, of course, decrease by its evolution by Riemann equation. So you see that I will cross different kind of zone where you have resonances. Okay, here I put the color correspond to different kind of value of the resonances. Okay, it's an exponential production. So it produce exponentially produce particle here, here, and here. And of course, the mode which is the lowest mode will have the more production because it will pass through the highest value of the parameter of the parametric parameter. N equal to correspond to quadratic potential. So that's if I put it in shape of for different value of coupling. You see that so this is rho phi, this is rho radiation. So you have the classical here that the region we saw before, okay, after several oscillation. But at the beginning, you see you have different kind of oscillation, and we pass through band. Here you see you pass through one band. Here you see another band. So the band you pass, in fact, produce your particle exponentially up to the moment where the radiation begin to reach inflaton, and something strange happen here, which is called the back reaction, because you begin to produce as many radiation as in inflaton. So you are not in thermal equilibrium. Look. After the evolution, go again in A-4 and A-3. So, but you have a region which is not in thermal equilibrium because the expansion still dominate on the scattering phi chi, but you have an exponential production. So you are not in thermal equilibrium, but your exponential production give you more or less as many radiation as in inflaton in the term of density, but it's not at all reacting because after you begin to come back to classical evolutions. If I look at my equation of states, you see that you reach a region where omega is 1/3, which means that the equation of state of the middle, okay, of both of them. And so you see that you reach a domain where you have a kind of radiation bath, and then you come back to the classical. So inflaton is kind of behave like a radiation, is like tracked by the bath. The bath want him to be radiated. I will tell you how it's happening, but they are not in thermal equilibrium. So this is this region here, okay, that I was discussing. Okay, so but these back reactions are quite important, and I will try to make you understand what's happening. So formally speaking, that's the effect of the field you produce on the condensate through the equation of motion. Okay, so the net effect is destruction of the condensate into 5 particles. So you go from a 5 condensate with coherent effect to a 5 particles. Okay, so which means that my inflaton itself will depend this time on the position. Okay, so you have a region where my inflaton field this time is not homogeneous anymore. So how it's happening? So condensate is on the left. Okay, I have a frequency which is m phi, and it's completely homogeneous. So it is, my representation is a space here. So it's completely homogeneous in space, and I can it's possible to interpret it as a sum of different oscillators which are coherent. This is what we usually do. So we transfer from both condensates to n coherent oscillators of density n phi, which is rho phi over m phi, okay, and frequency m phi. So I can define a set of field. I can define, it's my right, okay, and I can even define a density of field given with all having the same frequency. But if I produce different kind of particle with different momentum P1, P2, P3, okay, you see that this particle have different value of momentum, and when they will interact on the condensate, each of your mode, in fact, will become this time incoherent, and saying that each mode, depending, of course, on the type of momentum which is produced, it depends, of course, on the time of the redshift also. So it's quite complex. So you go from condensate to 5 particles. Okay, see what's happening here, for instance. You can see on this plot. So here the particle content of the inflaton, this is the condensate content of the inflaton. You see that it first is completely condensate, and the condensate disappeared, and then the 5 particles are produced. So after a value of scaling, this is a scale parameter, and you finish with 5, which is a particle. So it's quite difficult to see the difference because both behave the same. You have to be careful when you make some computation because you go from a classical field to a quantum field, but except that the mechanism is quite well known. So I can give an example. Yeah,
you have 5 minutes.
Perfect. So I just don't need more. So I will just try to apply it to a dark matter production, which is minimal. You can imagine it's gravitational scattering. So this is really the minimum you can imagine. The minimum you can imagine it is that you have an inflaton which scatter. Can be also standard model, whatever you want. You scatter, okay, and you produce standard model or dark matter if you want through the graviton exchange. So this is really, I would say, unavoidable. This production of matter or dark matter is unavoidable because this coupling exists. Okay, this is weak, but as it is proportional to the energy momentum tensor of the particles, you understand quite well that in the early phase of universe, the inflaton condensate has a lot of energy. So the momentum tensor and the component 0, 0, if you want, is quite large, which is rho phi, okay? So you will transfer the rho phi through the graviton to the thermal bath. And so this is unavoidable. Just to show you, we did it, for instance, in a paper which has been released 2 months ago with Simon. And we saw that if I put my density, in fact, of radiation, you see you reach a maximum temperature and you decrease just by the scattering, gravitational scattering. So you have a maximum temperature here, which is unavoidable. You see this temperature here. So for different value, it doesn't depend a lot on the type of potential you have for quadratic, quartic, or power 6. It's around 10 to the 12 GeV. And this temperature, maximum temperature, is unavoidable. This is temperature produced through the exchange of a graviton from the density of inflaton. Just to how to think why you have such a large temperature, which is unavoidable. So universe has passed through this temperature unavoidably. It's mainly because this process at the early phase of universe, just at the end of inflation, rho phi is around 10 to the 16 GeV to the 4. So this coupling is 10 to the 16 divided by m Planck, which is around 10 to minus 3. So it's like an effective coupling of 10 to minus 3. So that it's not so little, in fact. It's Planck reduced, But as it is proportional to energy momentum tensor, and at the end of inflation, this rho phi is quite large, you have an effective coupling, in fact, of around 10 to the 3, so 10 to 16 to 10 to 18, 19. So you transfer an energy quite effectively. That's why you have such a maximum temperature, which is quite large. Okay, this is unavoidable. So we know that the universe has passed through a temperature of 10 to 12 GeV. This is unavoidable. So this is the first result. And of course, you can even read the universe, because what is interesting with this process, you can also have a reading of the universe. You need for that, a power an equation of state of 5 to 7 at minimum. With this equation of state, in fact, the radiation you produce have a slope. In fact, when you increase the power of k, you can understand quite well that rho phi will have a slope which is larger, so it will decrease faster because it will be redshifted faster. And on the opposite, the radiation will be less redshifted, so you have a possibility to have a reading just by scattering of the inflaton. Okay, gravitational scattering of inflaton gives you the possibility to have a reading. This is also quite new. So you can at the same time produce dark matter and have reading through the scattering of inflaton, gravitational scattering of inflaton only. So this is really the minimal you can imagine. What we need to say that all what we say should exist. Whatever is your model you do, you have to include this diagram, because this production of dark matter is unavoidable in a sense, except if you don't believe in a graviton. But this exchange exists, and this exchange gives you, for instance, if you look now on dark matter, depending on the mass of dark matter, depending on the shape of the potential, you see that you can produce dark matter from 10 to the 10 GeV to 10 to 1 GeV, depending on the shape of your gravitational potential. Okay, so this is all on this line. You have the right radical balance. Here you overproduce, here you underproduce, but on all this line here, okay, for this mass of dark matter and this reading temperature, the radical balance is obtained just by gravitational exchange of a graviton. So to summarize, gravitational exchange of gravity production give you the possibility to have a maximum temperature, which is unavoidable, can give you a reading temperature and give you a production of dark matter, which is also unavoidable. So this amount of dark matter should be included in any kind of production of dark matter, because this is in any case produced in the early phase of universe. So that's a summary. What we did, so we just saw that, okay, this is the plot I was discussing. So I can directly go to the conclusion, because the summary is in the conclusion. So studying the details of dark matter production in the earliest phase of universe is important for dark matter production in freezing scenario, and I will say also for reading, as you can see. So this is my summary in a sense. So you can see that wherever you are in the universe, from instantaneous reading to non-instantaneous reading or to perturbative effects, you have to be careful in the sense of what you do in any case. That's okay.
Okay, thank you very much for your nice talk. So are there any questions, comments? Yeah, Kimiko.
Thank you very much for your nice talk. During the reheating, if the time passes, as you said, and the parameter set in the stable region go to the unstable region from the redshift, and the parametric resonance or preheating occurs.
I didn't understand the question. Can you repeat
sorry.
it? Yeah.
Yeah. You told that even the parameter set is in the stable region. If time passes during the reheating from the redshift, this parameter set go to the unstable region, and the parametric resonance occurs or preheating occurs. Did you told that?
I don't really understood the question. So what you call stable region? What you call stable region?
Yeah, you showed us that some
perturbative region. Perturbative region, maybe you mean.
I think the parametric resonance. I think you.
Yeah, parametric.
Yeah, parametric
Yes.
resonance, maybe.
Yes.
Yeah, as time passes. But instead, if the reheating time is not so long, is it possible that the parameter set doesn't go to the unstable region and preheating doesn't occur?
Preheating does not occur every time. That's your question?
Is it possible to avoid the preheating?
If you decay fast, right? If you have friends on the fast decay, right? Of course. Yeah, parametric resonance can also be avoided. First, from the value of the coupling, and you're right, you can suppose a fast decay. The main problem of the fast decay, you have to be careful also because you could have a too large, let's say, reheating temperature. You have constraint on the reheating temperature in a sense. So, but understand, yes, you can avoid parametric resonance, increasing the decay rate, for instance. Yes.
Thank you very much for your comment.
No, it's okay. Very good. Good question.
Okay, Songmok.
I think it is related to previous one. So actually, during the reheating, you included the inflaton decays by adding some effective friction term. So during the preheating, is it enough prescription to add the effects of the inflaton decay?
I don't still understand completely the question, sorry, but it's always possible to add the inflaton decay during preheating. I don't see why.
Because in that case is actually even the mass of the particles like dark matter, for example, Chi particles will changes very quickly, and I do not sure whether kind of decay rates are well defined in that early time. So
I don't see any problem to this.
Okay, so you are saying that just adding friction time would be enough to include the decays of the Okay. Yep, thank you.
You're welcome.
Okay. Thank you to Jan for your nice talk. Yeah, I enjoy it. So, okay, the next speaker is the Oleg Lebedev. Hi, Oleg.
Hi.
Hi. So nice to see you again online. So you can now share your screen.
Yes, let me try that.
Hi, Oleg.
Hi.
I made the introduction of your talk.
Thank you. One sec. Can you unshare, Jan? I don't see how I can share my screen.
So yeah, I think the Jan only shared already, right?
Yeah, I am shared already.
Yes. So you are free to share your screen.
It doesn't want to do it. I don't know why. That's weird. Okay.
Yeah. Yeah. Okay.
Hold on. Maybe I just log in.
Okay, let's wait for Oleg to come back.
If not, I can redo my talk. Huh?
You can continue.
Nice to see all you. Lebedev.
Okay, so like. Okay, now you can share. Is it possible?
Something has changed. I don't know. It doesn't want to share. I don't know what's happening.
Yeah.
I really don't understand.
So do you have a share screen button? You have a
Yeah,
button?
it doesn't show me the files. Okay, hold on, let me try again. Sorry, just a sec, let me try again.
The window does not pop up? Normally,
Nope.
no? Mm.
I think something wrong here. Maybe there is a problem with the firewall or something.
Mm.
Can you maybe open my file?
Then, okay.
There is something badly wrong here. I don't know. It has to do with security. It doesn't want to share. It never happened before. I have no idea why.
It's okay. Let me see. Okay. You want to ask me to change the pages, right?
Well, I guess I'll have to do that. I tried.
Okay, I think that.
I'm sorry.
No problem.
Yeah. Okay.
You can ask me to point out. I have my mouse here.
Yeah. Okay. Well, thank you very much, Hyun-Min, for inviting me. So I'll talk about collective effects, and my talk is related to the previous talk by Jan. And the main point I want to stress is that dark matter is often created by classical or semi-classical fields, which means that the corresponding occupation numbers are large, which requires special care when treating dark matter production. So next slide, please. Yes, so I will only talk about the completely minimalistic setup. I'll talk about direct renormalizable inflaton couplings, and I will discuss preheating, reheating, non-thermal dark matter production, collective effects such as resonances, back reaction, and rescattering. And I will briefly discuss the possibility of identifying the inflaton with dark matter. So this is based on a few papers from last year and my review from last April. So next slide, please. So let me define my framework. As I said, I will look only at the very simple possibility. So I want to extend the standard model with the inflaton. So we'll assume that the Higgs is not the inflaton, so we have to introduce an additional degree of freedom, which is a singlet scalar under the standard model symmetries. And in this case, the only renormalizable couplings of the inflaton to the standard model are written here. So this is the first equation. And these are renormalizable, consistent with all the symmetries. They're dimension 4 and dimension 3. And as such, they should be present on general grounds. So, and therefore, these couplings are expected to drive reheating. That is production of the standard model fields by the inflaton. So if you want to incorporate dark matter, the minimal option would be to introduce another a real scalar degree of freedom, which is denoted by S. And in this case, we can also write down very simple renormalizable couplings between the inflaton and dark matter. So they also could be quartic or trilinear. And in what follows, I will neglect possible couplings between the Higgs and dark matter because I'm interested in non-thermal dark matter only, at least in this talk. Next slide, please. Yes, so dark matter and the standard model fields could be produced by different combinations of couplings. So in case A, dark matter is produced via a quartic term, phi squared s squared, whereas the standard model fields are produced by perturbative decay of the inflaton into the Higgs pairs. And then there are various permutations of such possibilities, but I will focus on case A in this talk. Now, the result depends on the inflaton potential after inflation. So that is to say, we have no idea how inflation has happened. So we are agnostic as to the inflaton potential, but after the dust settles, the inflaton potential around its minimum is described either by phi squared or phi to the fourth. So phi squared is the typical possibility, and phi to the fourth, for instance, happens in the Higgs inflation or related models. So the main challenge in this business is to take into account collective effects. The problem is that quantum fields, such as the standard model fields and dark matter, are produced by a classical field. And so even though the corresponding coupling can be very small, the occupation numbers are large. So what appears in the amplitude is a product of a small number and a large number. And in the end, the process can be highly non-perturbative and also highly non-linear, which makes things even more complicated. Next slide, please. So let me look at the simplest possibility and discuss reheating and dark matter production in a phi squared potential. So suppose that locally the inflaton potential around its minimum behaves as phi squared. And suppose that dark matter is produced via the quartic term phi squared s squared, meaning that dark matter is produced only when the inflaton keeps oscillating, so right after inflation. And later on, this process stops because the inflaton decays and the corresponding coupling is very small, so that the dark matter cannot be produced thermally. So in this case, dark matter production takes place only at the very early stage, right after inflation, whereas the standard model fields could be produced much later via a standard perturbative inflaton decay into the Higgs pairs. So the basic mechanism was explained by Jan just now. So during the inflaton oscillation phase, the inflaton field goes through zero, and that makes the effective mass for the dark matter field zero, which implies a large non-adiabaticity, meaning that particles get created around the minimum of the inflaton potential. And so this is a very efficient mechanism that goes back to Linde, Kaufman, and Starobinsky. So the way to treat particle production in this case is to describe the dark matter field as a semi-classical field expanded in the spatial Fourier modes denoted by xk in the next equation, and write down the equations of motion for the momentum modes. So the equations of motion take the usual form. So these are the material equations for each separate mode. And the equation involves a couple of parameters, AK, which is a momentum dependent coefficient, and Q, which is the effective mass of the dark matter field, which depends on the inflaton. And the solutions to this equation can behave differently depending on the values of A and Q. So on the right, I'm showing a piece of the stability chart describing solutions to the material equation. So if A and Q are such that we are in the shaded region, the solutions just oscillate, whereas if A and Q are such that we are in the white region, the solutions grow exponentially. And the exponential growth of the amplitude implies particle production. Next slide, please. So one should remember, however, that the material equation is just a very rough approximation because it neglects back reaction. Also, it neglects rescattering because different momentum modes of the dark matter field actually couple to each other. This can be seen from the Lagrangian. Also, different momentum modes of the inflaton couple to other momentum modes of dark matter. So in fact, this is a very complicated process. So in order to understand how the system behaves, one needs to run lattice simulations, and what one finds is that unless the coupling between the inflaton and dark matter is very small, what happens is that the inflaton background gets destroyed by dark matter rescattering. So what happens is that you produce some amount of dark matter, and then it back reacts on the inflaton background, effectively destroying it. In this case, the system often becomes relativistic, meaning that the equation of state coefficient is close to 1/3. Finally, the system often reaches quasi-equilibrium already during preheating. So it never reaches full thermal equilibrium. However, it can reach quasi-equilibrium during preheating. So this behavior is illustrated in the two plots here. So in the upper plot, I show the energy fraction carried by a particular term in the Lagrangian versus time. So we start with a blue line, which denotes the energy fraction carried by the inflaton. So the darker line is I think the potential energy, and the lighter line is the kinetic energy, or the other way around. But in any case, so initially the total energy of the system is stored in the inflaton. So it's 50% kinetic, 50% potential. But after a while, you start producing a dark matter very efficiently, and it starts back reacting on the inflaton background and redistributes the energy fraction carried by the different terms. And eventually what you find is that basically you get quasi-equilibrium, meaning that each degree of freedom carries the same amount of energy, roughly. And the lower plot shows the evolution of the equation of state. You start with a totally non-relativistic system, meaning that W is 0. And as long as the system is dominated by the inflaton, W remains 0, but then at some point you produce enough dark matter, and it starts making the inflaton background relativistic. The equation of state shoots up close to 1/3, and then gradually it decreases because the inflaton is heavy and eventually becomes non-relativistic. So the point I'm trying to make is that the system is quite complicated, and even though you start with a fully non-relativistic system, dark matter production eventually makes the system relativistic. And so the equation of state is a complicated function of time. Next slide, please. So schematically, what we find is the following. So if you just have an inflaton and a phi squared s squared coupling to dark matter, what you find is that the energy fraction carried by the inflaton decreases over time. And at the end of the day, what you get is a 50-50 split between the inflaton and dark matter. And that's what I call quasi-equilibrium. And what is also important is that you cannot transfer more than 50% of the inflaton energy at any coupling. So no matter how much you increase your coupling, the split is still 50-50. So next slide, please. So I've discussed how you produce dark matter. Now we want to have a complete picture, and our renormalizable framework is sufficient to do that. So reheating can be described by late-time perturbative inflaton decay into the Higgs pair. So the usual perturbative formulae actually apply. And the decay width is characterized by the sigma, which is the trilinear coupling of the inflaton to the Higgs pairs. So combining these simulations and perturbative calculations, one can delineate parameter space leading to the correct relic abundance of dark matter. So this is shown in the plot. The different lines give you the right relic abundance at different inflaton masses. On the x-axis, we have the coupling between the inflaton and dark matter, which is responsible for dark matter production during preheating. And on the y-axis, we have the trilinear coupling between the inflaton and the Higgses. So as you see at low couplings, the curves behave non-trivially. So there is some non-trivial relation between the couplings, which can be described by a semi-classical approach due to Velinda, Kaufman-Starobinski. So this is parametric resonance and so on. So it's pretty straightforward. However, at somewhat larger couplings above a certain critical value, this approach breaks down because the system reaches quasi-equilibrium and becomes highly nonlinear. So even though you increase the coupling, lambda phi s, the dark matter abundance stays the same. And this behavior observed for all inflaton masses. So at this strong coupling, what one finds is that the relic abundance is given by a very simple formula. What is interesting is that the relic abundance is completely independent of the initial condition. So it does not depend on the initial value of the inflaton field, and it does not depend on the value of the inflaton coupling to dark matter. So the memory effects are erased by quasi-equilibrium, and the formula is universal. And what I should say is that this strong coupling in quotation marks is actually very weak. I mean, it's still something like 10 to minus 7, or can be even weaker depending on the inflaton mass. Next slide, please. So schematically, we get the following picture where we start with the inflaton, which carries 100% of the energy density. Then during preheating, if the coupling between the inflaton and dark matter is not too small, preheating is efficient and you get quasi-equilibrium, meaning that there is a 50-50 split between dark matter and the inflaton in terms of the energy density. Then we'll let the system evolve. And since the inflaton is heavier than dark matter, at some point it starts dominating and contributes 90 or 99% of the energy density. And then perturbative decay takes place. And the remaining inflaton energy density gets converted into the standard model radiation. And actually nothing happens to dark matter. Dark matter doesn't talk to the standard model because the coupling between the two is too small. So that's the picture we get, and we can get the right relic abundance and the right reheating temperature. Next slide, please. So I've discussed the phi squared case, but sometimes you can have interesting models such as Higgs inflation, where the inflaton potential around its minimum is quarter. So in this case, things are somewhat more complicated and even more interesting. So the inflaton equation of motion changes, and the inflaton oscillations are not described by the cosine function, but instead by Jacobi cosine. And the equations of motion for the dark matter momentum modes have the form of the Lamé equation. So the structure is very similar to the material equation. You have two coefficients, kappa and q. Kappa is the momentum dependent term, and q is the effective mass of dark matter. Except in the quarter case, the q coefficient is a ratio of dimensionless couplings. So in fact, you have a conformal system, and what it also implies is that even though the individual couplings can be tiny, the ratio can be large, meaning that the process can be very efficient and the perturbative approach completely breaks down. So in addition to that, the inflaton self-coupling produces inflaton fluctuations. So even if we set the coupling between the inflaton and dark matter to 0, still the inflaton background will get destroyed, and it will just get destroyed by production of the inflaton quanta in homogeneities. And production of the inflaton quanta is described by the analogous Lamé equation with a specific coefficient q, which is equal to 3. And 3 is not a small number, meaning that the process is very efficient, actually. And that one can also produce a stability chart, which is similar to that for the material equation. But what I want to emphasize here is that resonant dark matter production occurs already at tiny couplings. So the individual size of the couplings doesn't matter. What matters is the ratio. So if the coupling between dark matter and the inflaton exceeds the self-coupling of the inflaton, you have a very efficient dark matter production, and the system cannot be treated perturbatively. Next slide, please. So let me again emphasize this new feature. So inflaton fluctuations get produced in pure 5⁴, which was studied in detail by Hleebnikov and Tkachov 25 years ago. So what one finds is that if you look at the amplitude of the inflaton oscillations in the co-moving frame, the size of the amplitude stays constant over time, meaning that particle production is not very efficient. So nothing really is happening apart from just the expansion of the universe. But at some point, you produce a sufficient number of the inflaton fluctuations such that they start back reacting on the inflaton background and destroy it. So you see that at the end of the simulation here, which corresponds to the conformal time of order 800, the inflaton amplitude becomes smaller and smaller, such that most of the inflaton energy is contained in the inflaton quanta, that is to say, in homogeneities. And that means that the inflaton background actually decays very quickly, even in the absence of any other couplings. So if you just have a pure 5⁴ theory, the inflaton background decays and you have inhomogeneities. Next slide, please. And in this system, again, you can ask what couplings lead to the correct relic abundance. You can so this is shown by the lines in this plot. So sigma versus lambda as before, and you see that the lines are basically flat, meaning that you have quasi-equilibrium very quickly. Even if you increase the coupling between the inflaton and dark matter, you don't increase the relic abundance, and also the relic abundance is insensitive to the inflaton self-coupling. So the two different curves correspond to different inflaton self-couplings, and the result is the same. So again, this signifies quasi-equilibrium, meaning that there is no memory, and the relic abundance of dark matter depends only on the decay width of the inflaton into the Higgses and the inflaton mass. There is no dependence on the initial conditions nor the couplings. So what is also interesting here is that tiny couplings are sufficient to produce dark matter. So you see that the typical number is something like 10⁻⁻12 or 10⁻13, and the sigma parameter is shown here in Planck units, and if you convert it into electron volts, you get something like 1 electron volt. So you see that really tiny numbers are already sufficient to produce enough dark matter. And if your sigma is above this value, you simply overproduce dark matter and the model is ruled out. So that means that one has to be very careful when looking at dark matter production, and even really tiny couplings between dark matter and the inflaton can actually lead to unrealistic models. So you really have to keep it under control. Perhaps have some symmetry which would forbid such couplings. Next slide, please. Okay, so how much time do I have, Hyunmin? I can hear you. Can you show with your hand? 5 minutes or? Five or 10? Okay, never mind. Okay, so let me briefly discuss the possibility that
7 minutes. Sorry,
7 minutes. Okay, great. That the inflaton can be identified with dark matter. So we're still in the same framework, but we want to make it even more minimal. So instead of introducing 2 degrees of freedom, let's introduce just 1 degree of freedom, and assume that whatever drives inflation eventually plays the role of dark matter. So what is the setup? The setup is very simple. So you introduce the field phi, which is the inflaton, and you impose a Z2 symmetry on the inflaton such that it doesn't decay. And then you write down the most general renormalizable scalar potential. But in order to describe inflation, you need to introduce a non-minimal coupling of the scalars to curvature, similar to the Higgs inflation. So they, the action is in fact quite simple. So in this setup, inflation would be driven by phi, and if you go to very large field values of the inflaton, the corresponding potential in the Einstein frame is exponentially close to a flat one. So you get a very nice picture similar to Higgs inflation described by Misha. So, this potential is given in terms of the canonically normalized inflaton, and the non-minimal coupling to gravity here is not necessarily large, it could be small, so it still works. And this model would fit the Planck data very well. So that's another piece of motivation for this framework. Now we want to look at preheating. So basically, the problem is that in this model, the universe is totally dark. Yeah. So the inflaton drives inflation, but eventually it needs to generate enough standard model fields. But the problem is that it's stable, so it cannot decay. So the only way to do it is to produce the standard model fields, such as the Higgses, via resonance, so via preheating. So what we need to do is we need to look at preheating in the phi to the 4th potential, because that's what the that's what the potential is at small field values, and we need to look at the Higgs production in this quartic potential via the Higgs portal term h squared phi squared. So next slide, please. Here's what we find. So there are 2 options. Dark matter can be thermal or non-thermal. So let's look at the non-thermal option. So as I said, initially the universe is totally dark, so we need very efficient standard model production mechanism, meaning that the coupling between the inflaton and the Higgs has to be quite large. Otherwise, you just simply don't produce the standard model fields. So if there is no resonant Higgs production, then the dominant mechanism in the system is the production of the inflaton quanta, or the inflaton fluctuations, which is described by the Lamé equation with coefficient Q being 3. And what one finds in this case is that basically the 0 mode of the inflaton gets converted into fluctuations, and almost no standard model fields get produced. So this is a highly subdominant process. So mostly you simply produce the inflaton fluctuations, and basically those fluctuations stay there. Of course, you can compute the production rate for the standard model quanta via collision of the inflaton quanta, but the coupling is very small, so the system never thermalizes, and so simply you don't produce any tangible amount of Higgses or other standard model fields. So basically, in this case, the universe stays dark. Now, suppose we increase the coupling between the Higgs and the inflaton, so which leads to very efficient resonant Higgs production. But the problem is that if the production is efficient, back reaction kicks in and shuts it down. And so sooner or later, you reach quasi-equilibrium, and each degree of freedom gets the same share of the energy density. This is shown in this plot. So this is a result of our simulations. And basically, if you have just one inflaton and one Higgs field, and the Higgs field has 4 degrees of freedom, so you get 20% versus 80% energy split. So 80% is carried by the Higgs because there are 4 degrees of freedom, and 20% is carried by the inflaton. And even if you include all standard model degrees of freedom, you still get quite a lot of energy carried by the inflaton. But the inflaton is stable, so it stays there. And that leads to a lower bound on the abundance of dark matter. And then we find that the lower bound is something like 10 to minus 3. And this should be compared to the typical number required by observations, which is something like 10 to minus 10. But of course, it depends on the dark matter mass. Anyway, what we find is that even in this case, the relic abundance of dark matter is way too large, and you end up with a dark universe again. So the non-thermal option is not viable. So next slide, please. Now, another possibility is that dark matter is thermal. So what that means is that you dial the coupling between the inflaton and the Higgs to be very large, maybe even order 1 or something. The Higgs inflaton system reaches thermal equilibrium. So in this case, what you have is something like singlet scalar dark matter. So you thermalize the system, and then the inflaton can freeze out and producing the Higgses and so on. However, the problem in this case is that the direct detection constraints are strong, and they require the coupling between dark matter and the Higgs to be quite large, above 0.25. So this is the famous plot from singlet scalar dark matter analysis. And so since the coupling between the Higgses and the inflaton is large, the corresponding radiative corrections to the inflaton potential are also large. And what one finds is that such corrections actually destroy the inflaton potential. And then that leads to loss of unitarity. So the inflaton self-coupling becomes too large. So this option is not viable. Now, there is one exception to this statement. So the coupling between the inflaton and the Higgs doesn't always have to be very large. So if you're sitting at the Higgs resonance, meaning that the inflaton mass is roughly very close to half the Higgs mass, you can produce enough dark matter, or the annihilation cross-section is large enough even for small couplings between the dark matter and the Higgs. So values of order 10 to minus 4, 10 to minus 3 are sufficient to give you a large enough annihilation cross-section. So if you're sitting at this resonance, very narrow resonance, you can make this idea work. So in the very narrow mass range, thermal inflaton dark matter is viable. And of course, you can go to non-minimal models where you introduce more degrees of freedom. And in that case, of course, you can also make it work. Next slide, please. So maybe I will skip that. Okay, can you go to the next slide? So I'll just conclude so that not to overload you with information. So I try to argue that collective effects in dark matter production are essential simply because the occupation numbers are very large, which leads to non-linearities. So we find that that the inflaton dark matter system often reaches quasi-equilibrium, meaning that each degree of freedom gets the same share of the energy density. This cannot be described by a perturbative approach. And we also find that the minimal inflaton dark matter model can actually work, but only in a very fine-tuned mass range. So I'll stop here. Thank you.
Okay, thank you. for your nice talk. Okay, now it's open for questions, comments. I don't know if I can see some hands from you. Okay, Suro Kim.
So thank you for the nice talk. I have a nice question. So, do you know how the situation can be changed if we include the non-renormalizer couplings between the inflaton and dark matter?
You're talking about which situation? Are you talking about the inflaton dark matter model or something else?
Inflaton dark matter model, which includes the non-renormalizable couplings, like higher derivative couplings or.
So I think this will not change fundamentally, so probably the details will change. But the problem is that if you make any coupling between the inflaton and the Higgs large, you get quasi-equilibrium. But quasi-equilibrium implies that just like in thermal equilibrium, every degree of freedom gets the same share of the energy density. So at least right now, I don't see how this can change the conclusions. It can affect, of course, the thermal dark matter, so maybe the direct detection bounds and so on. But in terms of non-thermal dark matter, inflaton dark matter, I don't see how it will change things.
Okay, thank you.
Okay, are there more questions? Oops. Sorry. Don't know if I can see some hands. See, okay. Okay. So, okay, let me ask a question about the thermal dark matter case. I understand that in the case of non-thermal dark matter inflaton, you have a trouble with the dark universe because of the quasi-equilibrium will be reached at the end of preheating. So in the case of thermal dark matter, maybe you focused on the Higgs portal dark matter scenario. So if you have an extra annihilation channel for dark matter, other than through the Higgs, you might have, like for instance, if dark matter annihilate into the dark sector, still dark matter could be thermal equilibrium through the intermediate states. Then it might be possible, right? Without resonance, without including the resonance, without considering the resonance region, right?
Yes, that is certainly possible. So as I said, in the non-minimal case, you can do that. Even if you describe inflation in terms of the Palatini formalism, you can do that with a minimal number of degrees of freedom. So, however, my challenge was to see whether it's possible to have inflaton dark matter in the minimal case, because the whole point of the inflaton dark matter scenario is that you want to use as few ingredients as possible. Otherwise, there is no point, right? So of course you can introduce separately dark matter and inflaton, and that works. But my only motivation for looking into this inflaton dark matter business is just minimality. So I want to use a minimal number of ingredients. Of course, you're right. If you include a more complicated dark sector, you can satisfy all the constraints.
Okay.
But what is interesting for me is that you can still do inflaton dark matter in the thermal case if you're at the resonance. So it's still consistent, it's fine-tuned. So the inflaton mass has to be tuned to say like a few GeV. But it's still possible, even with the minimal number of ingredients.
Yeah. Kimiko, do you have a question?
Yeah, because I thank you for a nice talk. Because you told that going to the preheating and the dark universe happens. So it means that the decay width of infraton dark matter is not enough. So time passes and redshift occurs and unstable region going to stable region going to the unstable region because of the, as Professor Mambrini said, that decay width of infraton is not so large.
Yeah, you see, the thing is that there's no decay width. I mean, the inflaton is stable, right? So, yeah, because that's the whole point. You impose a Z2 symmetry to make the inflaton absolutely stable. Because it plays the role of dark matter. So the only thing that can happen is that at the early stage of preheating, so right after inflation, you have wild inflaton oscillations, and due to such oscillations, you produce Higgses, and you can produce them very efficiently. Okay.
Yeah, I thought that, yeah. How about the phi to the fourth potential cannot make the infraton condensate decay into the infraton quantum? I may miss something.
Yes. So it decays into inflaton quanta, but the inflaton quanta are stable. So they are dark, right? So before you had homogeneous inflaton field, and then it decays into inhomogeneous quanta, but then it's still completely dark. And basically, there is no mechanism to transfer this, dark energy into the standard model fields, because the thermal reaction rate is tiny because the coupling is small. So the only thing that can happen is wild preheating, but wild preheating is sensitive to back reaction. So if it's very wild, the back reaction is enormous and it shuts the process. So basically, sooner or later, you end up in quasi-equilibrium.
For example, is it possible for example, infraton condensate to quickly decay into the infraton quantum, and the infraton quantum quickly decay into the Higgs pair? Scattering and going to the two Higgs infraton quantum annihilate into the.
Yeah, but this is very small. Yeah, I know what you mean. So you have a collision of two inflaton quanta going into two Higgses. Yeah. So this rate is below the expansion rate. Yeah. So,
I see.
So the system never thermalizes. It's very small. So this rate is very small. So it's highly inefficient. Of course, you can do that if dark matter is thermal. So you can thermalize the inflaton system, and then this process becomes important. But that's a second possibility of thermal dark matter. And there, the problem is that there are strong direct detection constraints. So the coupling has to be almost order 1. So the inflaton quanta have to annihilate very efficiently into the Higgses. Okay. It has to be very efficient, but there is a direct detection bound. So those guys kill each other. They kill each other unless you're sitting exactly at the resonance.
I see.
Actually, I have a question maybe related to Kimiko's question. And normally, the previous work what we did is to take the effective kind of effective coupling between inflaton and the inflaton quanta itself, or inflaton and Higgs. So in the presence of the background field value for the inflaton is not near the origin, but if suppose the inflaton is far away from the origin, then even if you have a G2 symmetric self interaction for the inflaton, you could have effective coupling for the inflaton condensate. So in the presence of the background to inflaton field value. So because it's not in the true minimum, so effectively you are assigning some non-zero vacuum expectation value for the inflaton, such that you could allow the inflaton to decay. So this is the, I mean, the perturbative. We follow the perturbative calculation in the presence of this effective coupling between inflaton and two inflaton quanta, and inflaton and two Higgs quanta. So then we take the ratio of the branching, we take the ratio of the decay rate in the presence of this effective couplings. So, and then just this is perturbative analysis. And then just the dark matter production, I mean, dark matter abundance depends on the branching ratio of the decay rates. Just the standard model and dark matter quanta. So I think that this approach, but in your case, just to use the dark matter production is dominant near the origin when the inflaton crosses zeros, right? So when because the dark matter, the dark matter is
yeah. So basically,
yeah.
right. So if you want to talk about quantum effects of this type, the coupling has to be large. So the couplings I'm discussing here are small, so loop corrections are small. So you don't want to spoil the flatness of the inflaton potential.
Yeah. So yeah, of course if you don't have a non-minimal coupling, you don't the size of a coupling to inflaton might spoil the flatness of the potential. But somehow you can change the inflaton potential at the large field values, being compatible with the size of the couplings for the inflaton near the origin, because the shape of potential, shape of the inflaton changes as you go to the large field values for some reason. Then suppose in that case, I mean, the perturbative process might be important, but the preheating, I think I agree that the preheating effect might be also important, and because as you said, the inflaton fluctuation could be produced efficiently, and then it depends on the ratio of the couplings only, whether it is independent, whether the couplings are sizable or small. Just it depends on the ratio of the couplings, right? So I agree that the preheating is also important, but the perturbative analysis for the effective couplings might be also relevant. So this is because previously, before you publish your paper, there are several groups who studied this kind of rating analysis, right, based on this perturbative treatment, right? So
yes, but we disagree with those results.
Yeah,
as you know very well.
Okay, thank you. I think that I want to study this more, and I think that we want to learn more because of that. We are discussing now. So. Okay. I think that we are running. I think we have a sufficient. I don't have time to get more questions because of my too long question or comment. Okay, thank you. I think the time is running, so maybe we should end this session now. And thanks all the speakers in this session, Oleg and also Jan Mambrini. And Misha is not here anymore, but I thank Misha also. Okay, thank you.
Thank you.
We can see you again. Yeah, thank you. Bye.
Bye-bye. Thank you.
Very much.
Bye.
Thank you.
Bye.
Bye-bye.